So today our session chair for the first session will be Naumita Banerjee from IICR Bhopal. So I give it over to her now.
Okay, I welcome you all for the first session on day 2. Maybe we will just wait for a couple of minutes. It's 8:59 now, so let's wait for a couple of minutes and then we can start. Okay, so again, good morning to you all. So we are starting day 2, session 1 with Professor Rajesh Gopakumar from ICTS. And before we start, just I would like to request you to type up your questions in the chat box, until you want an answer at that moment itself, then definitely you can unmute yourself and ask the question to the speaker directly. And yeah, that's all. So let's begin. I don't want to waste any further time. So Rajesh, it's over to you.
Yeah, thank you, Naumita. You can hear me?
Yes, you are perfectly audible.
Okay, so thank you. And firstly, thanks to Ayan, Tane, and Suresh for putting together this workshop, a very nice workshop, a very exciting workshop in honor of David Gross. So it's a special pleasure for me to be speaking in David's honor since so sort of both personally and on behalf of ICTS. David has not only been my mentor and advisor, but also in some ways this talk and many of the things that sort of it's part of a ongoing effort for the last 15-20 years to understand the ADS-CFT correspondence. And I think I've had a lot of very wonderful conversations with David, and with his encouragement and inputs, I think it has been, that sort of helped a lot in this journey. And the journey of ICTS also, I think, has David very central to it. And he has been a pillar of support, first with Spenta and then with me. So once again, it's a terrific pleasure to honor David. And it was a pity that we couldn't have this meeting in person, because he was also supposed to come to ICTS, and then we were supposed to go to IIT Madras and so on. But yeah, hopefully it will happen later, thanks to the warm invitation of the IIT Madras director. So let me start on the talk itself, which will be largely based on this paper that we wrote recently, but I will try to set it in a bigger context. So the context will be that of deriving the ADS3 CFT2 correspondence, which I will say a little bit about, but not so much at length, since this is something I've covered in some talks, many talks recently. But what I would like to, so after laying out the context, I think some of these things will hopefully become more clear. But one of the things I would like to emphasize in this talk is that there's this particular example of the ADS3 CFT2 is something that relies on a tensionless limit of ADS3, which is described by a sigma model based on this supergroup at level 1. And this particular level, which is the tensionless level, has a very special free field realization, which I think is central to making this, to some of the simplifications and some of the underlying special features that you see. So in any case, I'll say something, I'll introduce that free field realization, and then move on to the central topic, the central objects, which are the correlators of this theory, which are dual to a symmetric product orbifold correlator. One of the things that will be, again, the thing that sort of the central message of the talk will be to try to show how a certain very unusual property of the worldsheet theory, namely a sort of localization on moduli space, follows from a certain relation which we've called the twistorial incidence relation, which I will try to explain. It's sort of like, for those of you who have some nodding familiarity with twistors, it's sort of like a twistorial relation, and I'll say more about that, and we'll see that that gives a sort of an interpretation to these free fields. These are sort of the bosonic fields here, and that enter into this equality. Finally, I don't think I'll have much time, but there is something that I'm actually super excited by, which is some work which is to appear. Unfortunately, I'm not in a position to talk about in detail, but this so far, everything that I said over here was sort of going from the worldsheet side and making a connection to the symmetric product orbifold. But one of the purposes of this example is to try to learn lessons to generalize. And actually, if one tries to go the other way around from the symmetric product orbifold to ADS3, one actually finds in a very natural way a realization of some of the ideas that I had been pursuing about 15 years ago in providing a general scheme of how to go from free fields to ADS. And so, but I'll just sort of basically say a few words about that, but that's something more for another talk. Okay, so let me just saying the context. So the idea is to consider a very special test case where one can understand the ADS CFT correspondence very this thing. So this is actually ADS3 CFT2. So one would like to understand this case explicitly, and there is indeed such an example which we proposed a couple of years ago, that ADS3 times S3 times T4, one of the canonical ADS CFT backgrounds, with 1 unit of NS flux, is dual to the large n limit of a symmetric product orbifold of T4. This is sort of what that looks like. So there was, as evidence for this, we initially showed the matching of the physical spectrum on both sides. This is the full spectrum of the theory, not some BPS sector or anything. And in a more recent work, we had been making the equality of the correlators. The dictionary of ADS-CFT is a large part of it is the equality of correlators of the, in this case, this is the Worldsheet ADS3 correlator, which is some integral over moduli space of physical vertex operators. Inserted at these points on the worldsheet Z1 to Zn, which you then integrate over. And these physical vertex operators are labeled by space-time points x1 to xn, which are the coordinates of the boundary sphere of ADS3. And so for simplicity, I've restricted to genus 0 correlators, but there's of course there's an extension to even higher genus. But this left-hand side, which is the string theory amplitude, is the ADS-CFT dictionary tells you it should be equal to the right-hand side, which is a correlator in a symmetric orbifold in the dual symmetric orbifold theory. So in this paper of 2019, we gave arguments to make this equality manifest, and I've described some of that in my strings talk, if you've heard that. So that's sort of the setting. What I want to emphasize, what I want to sort of go deeper into over here is to highlight firstly a very crucial feature of the worldsheet string theory that this tensionless string theory admits, it sort of has the property, namely that the localization of the left-hand side, namely this worldsheet correlator, to special points on the moduli space which admit branched covers. So the moduli space is that of the n-punctured sphere for genus 0. As I said, these are the coordinates Z1 to Zn. Normally you integrate over it. But for fixed Z1 to Zn, for a given point, actually you generically will not have any branched cover from the worldsheet to the target space, in this case, the boundary of the sphere, S2. If you specify these branching data and the fact that it should map to xi. So the existence of a branch cover is the existence of sort of a meromorphic function from the sphere, from the worldsheet to the sphere, such that in the vicinity of any of these branch points, Zi, with branching number Wi, which is part of the data, and W, I didn't really emphasize this, W's here. From the point of view of the string theory, they are the so-called spectrally flowed sectors. And from the point of view of the symmetric orbifold, these are the twisted sectors with a cycle of length W, and the W's, these respective W's are mapped onto each other as part of the dictionary of the spectrum. So in any case, in the vicinity of any particular point, Zi, with branching Wi, the existence of the branch cover should behave like this. And in general, this exists only on a codimension n-3 surface inside the moduli space of the n-punctured sphere. So in other words, to discrete points. And so that essentially means that the worldsheet correlator, before you integrate it, and so this is the unintegrated correlator, the physical correlator. Forget about all these pieces over here. The main thing I want you to focus on is that it has this localization, that there's a delta function localization on n-3. So n-3 delta functions. Let's say you fix 0, 1, and infinity, use Mobius invariance to fix 0, 1, and infinity on the worldsheet to map to 0, 1, and infinity in the target space. Then the remaining n-3 points, their images, supposing I fix this xi there, or if I fix the zi, then the images xi are fixed. They're not, you have sum over only a finite number of admissible covers, where this correlator is non-zero. So this is very different from what you normally have, for instance, in the free boson, free string theories that you in flat space, for instance. So the goal, one of the goals, is to understand the origin of this localization better, of this correlator, and to sort of show why it's a very robust property. So in our previous work of last year, we had argued for this localization using ward identities of the SL2R level K+2 theory, which is what describes the ADS3 piece in an NSR formalism. And of course, you have to be in the spectrally flowed sector, so the ward identities are actually quite non-trivial. They're not your simple global ward identities. They have to take into account the shift in the mode numbers of the currents under the spectral flow. So you have fairly non-trivial ward identities, and for k equal to 1, what we showed was that there is a solution to the ward identities, a very non-trivial solution, which has this delta function localization. But there could be other solutions as well. The ward identities just tell you what some constraints the correlators must obey, but it doesn't completely fix it. Moreover, we use this NSR formalism, like I mentioned, which strictly speaking breaks down at k equal to 1, because not the SL2R piece, but the SU2 piece has a negative level. And so though I think the NSR, the SL2R level K+2 ward identities, you can study them by itself, and the solution we found is a solution, but you might feel a little nervous that maybe at k equal to 1, something special happens, etc. So one of the things we showed here was that these correlators are indeed delta function localized. And for that, this free field realization and the hybrid formalism, the so-called hybrid formalism of Berkowitz, Waffer, and Witten, unlike the NSR formalism, is based on the supergroup at level k. And so we use the fact that at level k equal to 1, there's a free field realization, as I mentioned, which shows that the correlators are delta function localized. So it's not a solution. You can actually constrain the correlators enough to say that they must always have this delta function. And this suggests an underlying twistor string theory that I mentioned, the twistor incidence relation, I think is a signature of an underlying twistorial string theory, which I think would also explain some of these delta function-like localization. I mean, it does explain this delta function-like localization, but it probably shows that it comes from an underlying topological nature of this twistor string theory. So let me say a little bit about this, how this free field realization helps you to show this delta function localization. So many of you may be familiar with the fact that SU2 level 1 conformal field theories or Weizmann-Witten models have a free field realization. The PSU 1,1/2 is just a sort of a fancy supergroup, which has it has in fact an SU2 piece, but it also has SU 1,1, that's the SL2R piece, and then there are fermionic generators, and in fact I've written the generators over here. So the Berkowitz-Waffer-Witten hybrid formalism tells you that this Weizmann-Witten model describes the ADS3 times S3 piece, and then the T4 piece is fairly trivial, that's sort of more conventional. So the free field realization of this Weizmann-Witten model is in terms of two pairs of complex fermions and bosons. So normally SU2 level 1, you have a complex fermion. It's a C equal to 1 theory, and you have a complex fermion describing it. And that we'll see is in fact a part of it. But here you have not only these fermions, which I'll denote by psi and chi, but also the two bosons, which are actually spin-half bosons. So these are kind of what are called symplectic or spinorial bosons. It's like a beta-gamma system. So it has the wrong statistics. So it has a spin-half, or the wrong spin for the bosonic statistics. So just like for the free fermions, which give you actually a realization of U2 at level 1, here these fermions, you can see, in fact, that sits over here. The fermions generate, so these Ks are the SU2 generators. They're built from bilinears of fermions. There's a U1 current also. But now you have these bosons, so you actually generate also the SL2R piece. And then the mixed terms generate the super generators, and there's another U1 from the bosons, etc. So just like from going from U2 at level 1 to SU2 at level 1, you have to kind of take a relatively trivial coset, which removes the U1s to get the PSU 1,1. /2 level 1 theory. So this is one of the simplifications of this level 1 background that describes ADS3 times S3, which I think is key. And so as I said earlier, this is something we are currently investigating, how this how we can rephrase everything in terms of these free field realization, which makes the system manifestly a topological string theory.
Rajesh, can I just interrupt with a brief question?
Sure. Yeah.
Is this PSU 112 theory, is it a rational CFT or an irrational one?
So it is. This is a non-compact part. There's an SL2R piece which is sort of non-compact. So so in that sense, I don't know what you. There are infinitely many primaries, because once you include all the spectral flows and everything, there are. So unlike the SU2 level 1 piece, which is very, which is of course a rational piece. In fact, the representations I was just going to write down, there's infinitely many of these primaries, especially including the spectral flow. Though in some sense, it's sort of, it's some sort of a borderline, because there's a piece which is, they are essentially copies of a basic building block, which is these short representations. Which are the analog of the integrable representation of SU2 level 1. The SU2 level 1, as you know, has only a primary, which is a doublet, and then its descendants. Here you have there's a doublet, and then there's a continuous representation of SL2R. And
so there are primaries with all real dimensions, not necessarily rational dimensions.
Because this here there's a free parameter lambda of SL2R. So SL2R, unlike SU2, has these continuous representations where the J3 quantum number lambda is independent of the spin quantum number J. So unlike for SU2, where J means that the J3 quantum number is plus minus whatever, minus J to plus J. But here you have an independent continuous parameter lambda, which is the J3 zero eigenvalue. That's the SL2R eigenvalue. And because of that, the dimensions will vary continuously on this lambda. And then there is the spectrally flowed states and so on. So it's a much larger this thing, but in some sense, this is the building block. So everything, in some ways, it's very tractable, because it's sort of just this with labeled by this lambda, and then all its spectrally flowed versions. So that's what makes it sort of tractable. And in fact, this is very important, because normally in the ADS3 backgrounds, for higher flux, there are continuum states. There are states which are labeled by the J quantum number here. So the upstairs label is this J. So essentially, J is half or 0 or 1, whereas in general, we would have had J would have been half plus IP, and its multiplets, and there would have been this continuous thing, but we don't have here p is equal to 0, and then the super multiplet associated with that. So this is a simplification of the level 1 theory. So we need to add also the spectrally flowed states. I don't want to get into all the technical details, but essentially the spectral flow acts very simply on these free fields. It just, for each unit of spectral flow, you just shift the mode numbers up or down by plus minus half in some way. And this allows you to write down the OPEs of the free fields with the physical vertex operators. And these OPEs can be written down explicitly. I'm just writing down a couple of them involving these bosons, which because this is what will play an important role. They in this W spectrally flowed sector, you see that their OPE, the singularity depends on W, and that plays a crucial role. And it is from these OPEs and some of the others I haven't written that you can derive this twistorial type of identity for this bosons psi plus and psi minus, which underlie this free field description. So let me give a rough, very sort of basic picture of how this twistorial incidence relation, which is key, as I said, enters. So you actually look at correlators involving, forget about this piece. These are essentially the vertex operators. Because we are in a supersymmetric theory, there are some analogues of sort of picture changing, which I don't want to get into. That's relatively trivial, and they don't play their positions, and these things don't really enter. It's like usual picture changing insertions, but so forget about this piece. Just these are the physical endpoint function of the physical vertex operators, and then these are these additional bosons. So if I consider a correlator like this, which has additional insertions of one of these free bosons, and I normalize it to remove some of the obvious poles and zeros, you can then show that these quantities p plus minus are actually polynomials of a certain degree, which depends on W in the Zs. Those of you who know something about branch covers know that this is sort of the Riemann-Hurwitz formula for genus 0, and this n is actually the degree of the cover, total degree of the cover. But in any case, this is something one can show. And moreover, by looking at the OPE behavior, as I said, in the vicinity of, say, Z going to Zi, you can show that a combination of this P minus and P plus actually behaves like a branch. It has a sort of a very mild, it vanishes up to a very fairly order Wi. And this is true as Z goes to Zi. So in fact, if you pull out a piece which doesn't depend on Z, but can depend on Zi and Xi, which actually will be a distribution. If you pull out an overall factor, then what is left is actually regular polynomials. And these regular polynomials, in fact, you can show that they define for you a branch cover. This defines a branch cover because if P plus is not equal to 0, you have gamma as some ratio of two polynomials, both of degree n, and that's a covering map from a sphere to a sphere with branch points wherever this happens. So in fact, this identity tells you that these P pluses and P minus are essentially proportional to the polynomials that define a branch cover. So this just comes out of the free field OPE. So we didn't have to say anything about it was just from this automatically defines for you it gives you a sort of a branch cover very naturally, which has this branching behavior. Like I said, in the vicinity of Z going to Zi, there's a branching of order Wi, and the pre-image is, and the image of the branch cover is Xi at Z equal to Zi. Now, as I said in the beginning, the covering maps from this worldsheet, this n-punctured sphere worldsheet that we are considering, to the target S2, namely the X space, the X space over here, with specified branch points having this behavior where the branching data that I specified over here. If we consider these covering maps, they exist only on a codimension n-3 subspace of this moduli space, i.e., it's a discrete set of points where you have support, and in fact, this tells you, if you put these things all together, the things that I just said over here, if you put them all together, what it means is that this psi minus, so if there's a branch cover gamma, then the psi minus and psi plus obey this. So in some sense, the psi minus and psi plus sort of, this gives an interpretation, which I'll just come to, as some kind of twister-like variables for the space-time S2. This is a sort of an identity in physical correlators, and this is what we call the twistor incidence relation, and I'll say more about this soon. But I wanted to, before I explain the name twistor incidence relation, let me say a little bit about how this immediately implies, this relation is sort of the key to actually constrain the correlator and give this delta function-like property. Because the localization then follows, because you know, firstly, that, as I said, the branch covers themselves exist only on this codimension n-3 subspace, but you can see what the precise nature of the localization of this correlator is, because it follows from the definition that I wrote, that you have something like this, and at Z equal to Zi, for the other, if I fix 3 points, 0, 1, and infinity, for the remaining n-3 points, you have some relation like this. This immediately implies that this distribution is a sum over delta functions, sum over products of delta functions, using the fact that the sort of the distributional solution for x f of x equals to 0 is f of x is proportional to delta of x. So, in fact, these twistor relations constrain the correlator even more. They determine the dependence on the conformal dimensions, the ones that Sunil was asking about, the h's and so on, and then but then there's this. So you get this delta function-like behavior, and you have a sum over this discrete number of covering maps that exist, and you so the correlator is a sum of these. And in fact, from a separate argument, one had in our previous work combined this delta function. There we had, as I said, obtained it using ward identities. We had sort of found that there was a solution which was similar, but there we also combined that then with a different strand of argument using a semi-classically exact solution for the sigma model, which gave you the result that this was essentially proportional to Liouville action. And this is sort of the Lunin-Mathur. From the point of view of the symmetric orbifold, this is the sort of Lunin-Mathur action, but now coming out of an ADS3 sigma model, so that you have And this log, in fact, it's a Liouville action for a bosonic field, which is given by the conformal factor of this map, namely log of mod del gamma square. So that was that in fact constrains this as well, and makes the equality to the symmetric product correlator manifest after you integrate over the moduli space and pick up just these discrete contributions. So that was the localization. So what I wanted to, the message here is that the localization constraint, this twistorial identity immediately gives rise to this delta function localization and constrains the correlator in a way which is much stronger, much more powerful than what the word identities could do earlier, and which show that in a sense this free field version is the one that captures all the special properties of the level 1 theory, the k=1 theory. So now let me try to say a little bit about why twistorial, why I was making the connection with twistors. So firstly, there's a kind of a similarity between this this combination, or I guess, that combination here and that appears, and the usual twistor relation, which in 4 dimensions you might have seen. It's something that relates to spinorial variables to the position x's written in the bispinor language. So this psi plus and psi minus here are playing the role of these spinorial variables. In fact, they are exactly like that. They are bosons, but with spinorial transformation. And these x's are essentially gamma, because gamma is x of z equal to gamma of z is the target space, is the map to the target space. So that's what this is. I mean, this gamma of z is essentially mapping you to in the conventional NSR type sigma model, the x's are really equal to gamma of z. So, but okay, so this is sort of similar, superficially looks similar, but more fundamentally, I think if you look at the free field action, you can write down the action. I wrote down the generators, but you can actually assemble all these fields that I mentioned into sort of 2 sets of super twistor fields, these free bosons and free fermions that I had. And if you write down their action, and provided you actually gauge the current, which goes from U1,1/2 to PSU 1,1/2, then the action can be written in a very compact form. This is the left moving piece, and then there's a right moving piece, or written out in full. It is that, and this is actually the strict analog of twistor action. Sorry, that had been proposed earlier by Berkowitz for describing amplitudes of 4D super Yang-Mills theory. There you had just double the set of variables. You had PSU 2,2/4 super twistor variables. You have sort of half the PSU 1,1/2. And Berkowitz, building on the work of Witten on the twistorial formulation of super Yang-Mills amplitude, had written down this action, which he showed reproduces the twistorial properties of these MHVA amplitudes, etc. And it has the similar delta function like localization over there. And so it suggests that this is the right way to think about the underlying topological string theory that describes this ADS3 in this tensionless limit, and also suggests how to generalize it. So finally, in the last couple of minutes, so that was sort of what I wanted to say about this. The central thing was this twistor incidence relation, from which all the good things follow, and which suggests this twistorial sort of language is the most natural geometric picture, because what you lose when you go to this free field realization is the obvious geometric interpretation of these free fields, because from a CFT point of view, it's some algebraic trick that you use to write the CFT at level 1 in terms of these free bosons and free fermions. But this gives you an underlying geometry that you're actually looking at sort of a twister-like formulation of the space-time theory. So in any case, so that I think is very promising. As I said in the beginning, and so I'll be very brief here, we have been looking here the worldsheet theory on ADS3, a bona fide worldsheet theory with NSNS flux, and showing how it localizes onto branch covers and gives all the answers which I expected of the symmetric product correlators. So now I think we've sort of that argument from that side, we are sort of tightening all the arguments, which show you that this is indeed what the symmetric product correlators give you. But again, the whole attempt, as I said, is to see how we can learn lessons from here, which can be generalized. So you can ask the question, which sort of one might ask of free field theories in general, and that can we start from the symmetric product correlators and somehow construct the worldsheet string theory on ADS3, now that you know what you're aiming for and so on. And in fact, there are an associated set of Feynman diagrams that these correlators obey in a very nice paper of Parkman, Razamath, and Rastelli from over 10, 12 years ago. So using the branch covers and the associated Feynman diagrams, so the branch covers, so each branch cover has a sort of a diagrammatic meaning in this language, and the poles of gamma are related to the faces, and the vertices are related to the zeros, etc. And actually, it turns out that this very nicely realizes an old proposal of how free field theories can sort of, the Feynman diagrams of free field theories can glue up into string theories. In fact, a very non-trivial feature, which I was particularly, it was sort of amazing for me to see, is that the proposal was to sort of go via a certain Strebel parametrization of moduli space, a very special parametrization involving the existence of certain quadratic differentials called Strebel differentials. This parametrization comes out very naturally from this point of view, and in fact, it reproduces, that's how the sort of the string theory comes out. And in fact, the Nambu-Goto action can be written in sort of the Strebel gauge, and that is related to the weights that come out. So in any case, as I said, that's something for another talk. So let me just wrap up since I've gone a little over time. So the messages I wanted to get across was the delta function localization on moduli space. That is a necessary feature for this connection between the ADS3 string theory and the symmetric product orbifold. For that to work, this delta function localization is a very robust feature, which earlier we had argued using word identities, but were not able to uniquely pin it down. But now it's uniquely pinned down in this free field realization, because that sort of captures the essential features of this theory. And this has a very natural twistorial interpretation, as I said, and the aim is to connect that to an underlying topological string description, which would explain all these delta function-like localizations in some worldsheet point of view. And finally, going the other way, starting from the symmetric product, I just stated this, you actually recover the string theory in a very special parametrization, this treble parametrization. But let me stop over here and see if there are any questions.
Okay. Let us all unmute and thank Rajesh for this wonderful talk. So there were two questions. One was from Suresh. So Suresh, please unmute yourself and you can ask the question. Yes.
Hi Rajesh. In general, if you look at the model space of hyperelliptic curves, which are, if you wish, branch covers representation of genus G greater than 1, that model space is I think, codimension G, about codimension G in the full model space. So in your equality, where you only discussed today, of course, the genus 0 case, what I have in mind is genus 2 upward. Do you think this delta function localization will always localize onto branch covers or hyperelliptic curves in general?
In fact, this generalization was done by Lawrence Eberhardt earlier this year. So he argued using not the free field realization, but this word identities in quite a technical tour de force. He argued using the properties of the differentials, the various the covering maps on the genus G surface, and that you get localized to points. So indeed it has the right codimension, and that it is localized to points, because it's not only hyperelliptic curves. That's one class of branch covers, but you can have more general branch covers. And if you look at all the allowed branch covers, then it does localize to these
so
points.
You mean higher degree, not just square root branch?
Yeah, exactly. Higher degree branch, because in general you have to sum over all. The degree depends through this Riemann-Hurwitz formula over here. So so once I specify the W, the degree is fixed, and in general it's much greater than 2.
Can you share the link to Eberhardt's paper in Slack later?
Yeah, I'll do that. That's I think February of this year, but I'll
okay. Thank you.
Sharon.
Thank you, Suresh. And there was another question from Shiraz. Shiraz, please unmute yourself and ask.
Really beautiful talk. One question, just to make sure I'm understanding right. Suppose the boundary was a sphere, and the worldsheet was also a sphere.
Yes, that's the case we are considering. Yeah.
Great. So the primary operators are inserted at particular points on the boundary sphere, and naively you would say that they were integrated over all points on the worldsheet sphere. And so you're arguing, did I understand right, that you're arguing that this correlation function is just 0 unless the insertions on the worldsheet sphere are at the same points, up to, I suppose, overall rotation as the boundary sphere? It's just 0 as a correlation function. And
exactly, that's what this delta function tells you.
I see. So now this is only within BRST cohomology. I mean, I was trying to understand how this agrees with general expectations of OP and so on.
Right. So we haven't done it in a BRST way. This is sort of, if you wish, the analog of the old covariant quantization. So you have a particular choice of vertex operators, and then in that particular, so in some sense you've sort of fixed to conformal gauge, and then you've sort of done it. So these are the correlators in that framework. But in some sense, this is what we are currently trying to do, starting from this sort of twistorial action and so on, is develop a whole BRST formulation where you'll see this sort of in a more, perhaps in a more global setting.
Right. I'm trying to understand. The normal expectation of a CFT is you bring two operators together. There's some sort of singularity. There's an infinite number of terms. I'm trying to understand how that is consistent with.
So the Z dependence is there. I mean, this is so if I bring Z1 to Z2, then there are additional Z dependencies over here and here, which actually capture the OPE behavior. So notice that this is just I mean, there will be, I mean, as you, if you, so it's this is not quite the same. This is a sort of a little bit of a transcendental relation which relates the Zi, I mean, the delta function is not between the Zi's, it is between the, I mean, not directly between the Zi's, but between the Xi's and the Zi's. So there is a piece which captures all these OPE data, which is, so this sort of OPEs are all there on the worldsheet, but there's a sort of a global constraint, which is the thing that relates the X's, which are properties of the vertex operators with these Z's. And some of these delta function, this sort of overall delta function-like behavior also is a property in topological string theories. So you get the same sort of the same. But I think a BRST analysis will help to show this, because this is perhaps, there's perhaps a way in which this will be less singular. This is in some sense a sort of certain singular gauge in the worldsheet. And that's why you have some of these additional constraints. But indeed, there is the regular OPEs, which is what underlies all this. But there's sort of a global constraint. I don't, yeah, that's sort of the best I can say.
I was wondering whether there would be another picture, maybe you're saying in some other gauge, in which the correlation functions are non-zero everywhere, but they're sort of like total derivatives.
Yeah, yeah, exactly. That's what I think a BRST picture will hopefully tell you, that there's sort of less singular, but they're kind of derivative terms which don't in the end contribute.
Total derivatives of something that has a singularity at these special points, and so only contributes at these special points.
Yeah, yeah. In some sense, the worldsheet, this treble gauge gives a sort of a worldsheet metric which is sort of singular at these points. You have curvature singularities precisely at the insertions of these points. So yeah, but I think that's why it would be very useful to understand that in some distinct way. But if you look at any topologically twisted sigma model, some of these properties are also there in these topologically twisted sigma models. So
and there as well, the BRST condition is key, right? As just conformal field theories, it wouldn't happen, but it's because we're looking at BRST cohomology.
Yeah, we are looking. The physical state conditions are actually key to having this. You have to look at the states which obey the physical state conditions. So so here the free field realization, we impose then the physical state conditions to get this sort of behavior. But even in a conformal field theory, you will have, that's what I wanted to say, that in a conformal field theory also, which is topologically twisted, because of the nature of the topological twist, you often have these delta function-like behavior.
Yeah, I was thinking of the twist as being an imposed BRST condition. Right? Things are annihilated by this Q charge. Sort of like
no, I mean, you can talk of a sigma model without coupling to gravity.
Yeah, no, I meant just the twisting itself could be thought of as imposing a sort of BRST condition. States annihilated by Q.
Yeah. I mean, that's roughly how it works out. I think that's roughly how it will work out in this particular case, because the underlying the worldsheet physical theory itself is sort of a twisted theory. So the Q is what sort of does that twist. That's completely correct, I think, as to how it will work out. But yeah, but I can only see the sort of the broad contours of it. I don't know the details.
Okay, one quick follow-up, if that's okay. In the case of SU2 free field realizations, you can realize level 1 with the single complex free fermion. Then you can also realize level 2 with 2 complex free fermions. So I was wondering whether something similar was true of your supergroups. Can you realize all the higher Ks also with multiple copies of your matter content?
But they're no longer free, right? They will have some background charges or something like that in general.
In the case of SU2, it was just completely free. Right?
Sorry?
It's just, in the case of SU2, you could do it with completely free fermions. Right? Just double up the copies and you get
but not for arbitrary level K. Only if you are adjoint. I mean, there's this. You can do it for special levels.
Oh, I see. Maybe I'm missing.
Because in general, it is 3K over K plus 2, right? The central charge.
I was just thinking that if you take J as the J of the first group of fermions and plus J of the second group of fermions, then won't the level just add?
No,
J
no.
is equal to J1 plus J2?
No, I don't think so. Because the central charges don't add. So it's not a Sugawara type, this thing.
I see, but then some modding out? Because
Yeah,
K
there
seems to add.
Yeah, I mean, there are some free field realizations. They're more complicated. They're not like simple free field, this thing. Maybe someone like Sunil may know more.
You would have a higher level K algebra, right? Current algebra.
Yeah.
Because K just adds.
Yeah.
And then you may have to mod out some to remove some.
So there may be this thing. It may not be so simple, but it is. Yeah, it's right. Like for SU2 level K, there are. You can write it in terms of bosons with a background charge and so on.
Okay. I was wondering if you could do that.
Sorry, just 1 second, Shiraz. I must say, level 2, there is something very interesting which I haven't at least thought about, and that is the SU2 in the NSR formulation. The SU2 has level 0, so so it is sort of, I think, halfway between this K equal to 1 and the general K. There's something special happening at K equal to 2 also, but I don't know the.
Yeah, I remember your papers on that. Yeah, I was just wondering whether you could, build at least one other case and see the contrast. See from that point of view why K, how there's much more away from K equals 1.
Yeah, I think what would be most useful for doing this contrast is actually to turn on Ramon-Ramon flux. Because that is a continuous deformation and that you can actually do, because the quantization of Ramon-Ramon flux you do not see at weak coupling, and therefore you can continuously deform it, and I think these delta functions will continuously get deformed in that picture when you turn on an infinitesimal Ramon-Ramon flux. So that, I think, is an interesting question which you can frame in the language of this free field theory, but as a continuous deformation. It's perhaps a somewhat tricky singular deformation, but it is, but principle, if dealt with correctly, you should be able to see somehow this delta function gets smeared out, and at the same time, you do not have a continuum. So that, I think, helps you. Because
the worldsheet to turn that on?
Sorry?
Do you know how to turn on the Ramon-Ramon fluxes on the worldsheet?
Rajesh and Shiraz, I'm very sorry to interrupt this discussion, but I'm extremely sorry. Can you please continue it like in Slack afterwards?
Sure. Yeah.
But sorry, Shiraz. But before I finish it, there were 2 quick questions, so I'll just take that from Shomangshu and Raghu. Please go ahead and please try to finish in 2 minutes.
Hi, Rajesh. Thanks for the nice talk.
Thanks.
So you just mentioned briefly that there is this beta gamma free field realization, the Wakimoto, and this Wakimoto is believed to be true, still holding for K equals 1 at large, because your worldsheet is sticking to the boundary at large phi. Could you arrive at the same conclusion starting from the Wakimoto?
So in some ways, in our previous paper, we did phrase it partially in that language of the Wakimoto. By the way, I should say this, when I said beta gamma, that referred to this system here, which is different from the beta gamma of the Wakimoto. I mean, that is, these bosons are different objects. And the mapping between them, in fact, is a little non-trivial. But the beta gamma system, yes, I think you can, and I think there was a follow-up paper by Hikida and so on who were trying to constrain the correlators that way using more directly the beta gamma system. But in principle, the thing is, the limitation of that approach was that we could use the WAD identities only, which are powerful, but not powerful enough to uniquely pin down the correlator. Maybe you combine that with the beta gamma system in some way, you might be able to, some additional this thing, you might be able to pin it down completely. Here, we didn't have to do any work because this gave you directly, I mean, we had to do some work, but it directly gave you the correlator. It constrained the correlator very powerfully, at least enough to show this delta function behavior. Yes, but I would say there is a possibility to use the beta gamma system in general and see this thing. In fact, it is interesting if you see, no one has probably read Maldacena and Oguri's third paper on correlation functions, but if you see in one of the appendices, in a footnote to one of the appendices for the 4-point function, they actually claim for the simplest case, W's are all 0, that they also found a delta function-like solution, but they said that no, but anyway, there is the other solution, and that's probably the physical one. So they had this thing. So, but in general, what I mean to say is that for general K, also there are for very special configurations, you find these delta function solutions. In general, they are probably not physical, but you have to, maybe it's good to understand that better.
Okay, thank you. Thank you very much.
Raghu, please unmute yourself and ask your question.
Okay, thanks. Hi, Rajesh. I just had a quick question. So am I right that this derivation that you presented is for endpoint functions on the sphere?
Yes.
Only, or? And so I know Lawrence has a paper.
Yeah. You're talking of the worldsheet, the space-time?
No,
or?
the boundary sphere.
The boundary sphere, yes, we took the boundary to be a sphere. In principle, you could generalize it because the Lunin math, I mean, okay, you would expect a similar covering space like this thing to exist in those cases. I think you might have seen Lawrence Eberhardt had a paper where he talked about the partition function on with higher genus boundaries.
On torus, so I guess his computations were on the torus boundary, and
mostly
there also
on the torus, but torus are orbifolds and so on. So it's more complicated technically, but I don't see any obstacle.
Okay, but the proof might, is it fair to say that the proof is still pending for the genus 2 observable?
For arbitrary boundaries, this is, as I said over here, it's boundary is an S2.
Okay, thanks.
Okay, thank you everyone. And let us thank Rajesh again for this talk.
Thank you.
Thank you, Rajesh.
Yeah, let me try to stop this screen.
Yeah, so now we can move on to our second speaker for the day.
Hi.
So, hi. So can you just share your screen?
Yes.
So our second speaker for the day is Gustavo Turiaci, and he will be talking on the gravitational path integral near extremality. So we are very sorry that we are like some 6 minutes delay, but hopefully it should be fine. So you may start.
Can you see the slides?
Yes, it is perfectly fine and you are audible.
Okay. Okay. Thank you very much for the invitation. It's an honor and a pleasure to participate in this conference for for David Gross. And yeah, I will be talking about the gravitational path integral near extremality. So, yeah, okay. So first, let me give a quick summary. So I will be interested in near extremal black holes. So we will look at black holes in some asymptotically d-dimensional space, which could be ADS mostly or flat space. And we will look at some charged black hole at low temperatures, such that it develops along ADS2 throat times some compact space describing the horizon. And the main feature that I want to point out, that it has been pointed out in several papers in the literature, is that in this limit, the gravitational path integral has a universality, and the relevant physics at low temperature is captured by Joaquin-Turiaci gravity, which is a two-dimensional dilaton gravity. And this has been done mostly semi-classical, and maybe the new thing I want to say is that there is a sense in which one can trust some quantum effects but when you are very close to extremality that are captured by JT gravity as well. And some examples that I will describe: the rotating BTC black hole in ADS3. So here, this MD would be ADS3, and the throat would be ADS2 cross S1. And okay, the charge would be the angular momentum. And another example would be a charged black hole, Reiser-Nordstrom, in asymptotically flat 4 dimensions, for example. Another point I would try to make is that in pure 3D gravity, there are certain non-perturbative effects that are also captured, not by JT, but by the deformations of JT. So I'm going to talk about that as well. Okay. So first, I will do a brief outline of the talk. So I will begin describing the ADS3 case. And this is based on a paper with Annemiek Ghosh and Henry Maxfield from last year, both from, well, Annemiek was in KITP and Henry from UCSB. Then I will mention these non-perturbative corrections in pure gravity based on this paper with Henry from this year. And then I will spend some time giving more details about these deformations of JT gravity, which are interesting by themselves. And this is based on the same paper and also independent work by Witten, and also building on some paper we wrote last year with Thomas Mertens, where we started studying this problem. And if I have time, I will mention some work in progress with Michel Satiuk from Berkeley and Wayne Weng from UCSB. Finally, I will briefly mention aspects of the case of 4D Reiser-Nordstrom based on this paper with Luca Iliesu, and some work in progress with Heidemann, Iliesu, and Shaw. Okay, so let me begin with 3D gravity. So we will consider 3D Einstein gravity, possibly coupled to matter, but I will focus on the gravitational sector for now. And we will be interested in the Euclidean path integral with the torus boundary conditions. And the classical solution is BTC, motionally the rotating BTC black hole with some mass E and angular momentum J. And this is the metric, is very well known, so it depends on the location of the inner and outer horizon, R plus and R minus, which are given as functions of the mass and angular momentum that are very well known, so I'm not writing it down. And the extremality bound tells you that the mass has to be bigger than the absolute value of the angular momentum. So the limit we will be interested in, the near extremal limit, is when the temperature of this black hole goes to 0. And for this to happen, the mass has to be very close to the angular momentum. And in this limit, the size of the inner and outer horizon are very similar. And I will denote the extremal quantities by R naught. But we will always work at some finite but small temperature. And in this limit, the metric is approximately, as I said, ADS2 cross S1, and this is how it looks like. So here I traded the radial coordinate R by rho, but it's the same. So this is a ADS2 factor involving time and the radial distance coordinate with some ADS2 radius. So sorry, L3 is the ADS3 radius, and this ADS2 radius is related to it in this way. This R naught is the size of the horizon. Phi is the coordinate along the horizon, it's DS1. And then it's not really a product. There is also this extra term coming from the rotation that I will interpret in a moment as a background U1 gauge field, because I'm going to do a reduction on ADS2. And the geometry looks like a hyperbolic disk. This blue disk, there's ADS2, where the angle is Euclidean time and times some S1 with the horizon. Okay, so semi-classically, what is the answer for this Euclidean path integral? So first of all, the extremal energy and Bekenstein-Hawking entropy are given by this. So the extremal values is for the energy, the angular momentum, and the entropy is the area over 4g Newton, which is which I wrote in terms of trading g Newton by the central charge c and trading the size of the horizon by as a function of the angular momentum. If we look at the Euclidean path integral, that is a standard problem, and look at the thermodynamics derived from them, then we get this result that the energy approaches quadratically with the temperature and the entropy approaches linearly with the temperature to extremality. And I wrote it in terms of this parameter gamma, which for BTC happens to be C over 24. But this formula will be more universal, and this is kind of captured by classical JT gravity. Okay. So in this limit, we want to study the dimensional reduction in the throat. So the idea is that we will rewrite the 3D theory as a 2D theory, which will have the original matter, the S in the S wave, and also KK modes. But the important thing at low temperature is to identify the massless modes, because those will be the relevant ones. So first we have the two-dimensional metric in the time and radius coordinate. We have the dilaton, which is the size of the horizon, and this U1 gauge field. And if you reduce it from 3D to 2D, to ADS2, you end up with the Achúcarro-Ortiz action, which is a dilaton gravity coupled to this gauge field, U1. But we can even simplify it further. First of all, 2D Young-Mills is a very simple theory in a way, or at least, well, this case is U1, so it's even simpler. And we can integrate it out exactly. And so we could do fixed chemical potential, which would be like fixing the angular velocity, but it's simpler to fix the charge, which is like fixing the angular momentum in 3D language. And when we do that, integrating out the gauge field gives a simple action, which is still local. And it's a dilaton gravity theory with a dilaton potential that depends on the angular momentum in this way. The second simplification is to realize that we have a approximately constant dilaton background in the throat, where the dilaton from this 2D theory is found by the equation of motion, which tells you that when the dilaton is constant, then the dilaton potential vanishes. And this phi naught, basically solving this equation gives you the size of the horizon as a function of the angular momentum. But now we want to study fluctuations, and we will focus on small fluctuations around this extremal size. And we will introduce this field little phi, which from now on I will refer to that as the dilaton. And we can simplify the action further by expanding around phi naught, and we get this. And so this is the first term, is a topological term where chi is the Euler characteristic, and it's not is the Bekenstein-Hawking term. So this is the term that will give you the extremal entropy. This linear term is the Chakib-Titled gravity. Okay. And the important thing, so here there will be other nonlinear terms, but they are suppressed by phi naught. Phi naught is of order j, or actually square root j. So the important thing is that this phi naught is very large. We will take very large angular momentum. And then all the higher order terms are suppressed. And this effective Chakib-Titled mode controls the breaking of the, so when you have an ADS2 that emerges in the throat, there is an emergent conformal symmetry. But an important realization of after SYK, for example, is that it's important that the symmetry is broken. Otherwise, the theory is not very good. And this mode captures the breaking of this conformal symmetry. And this reduction was studied also, like I mentioned, this previous paper by this group. And we also studied it last year with Ghosh and Maxwell. Okay, so as I said, we want to study the gravitational path integral fixing with the boundary torus, where we want to fix the temperature and the angular momentum. So the final result looks like this. So we have this e to the minus beta e naught. This contribution comes from, so if you imagine the geometry like this, you have the throat here, and you have here the asymptotically ADS3 region. When you do the path integral in the asymptotically ADS3 region, where you have to be careful with where you are particularly dividing the geometry and which boundary terms you used, the answer here is very simple and just gives you this term. Yeah, I should have mentioned it here, but this is also based in some paper of Trivedi and collaborators, but I think I will mention it later. And then we'll do the path integral in the throat, which is given by this Joaquin-Turiaci gravity, and this gives this e to the s naught. So here, the in Euclidean space is a disk, so that's where this term comes from. If you remember, this was multiplied by the Euler characteristic, and then we have the path integral over the 2D metric and 2D dilaton in the hyperbolic disk. And being careful about how to glue with the asymptotic region, we can find the boundary conditions. So if we put this blue line where we glue the throat with the faraway region, very far from the horizon, but such that it's the ADS2 approximation is good, you found that basically you want to put Dirichlet boundary conditions on phi, and L here is the Euclidean time circle. They are both large, so that's why this parameter, this cut of epsilon is going to 0, but the ratio is fixed. So they both diverge as 1 over epsilon. And the ratio between them, or this C over 24, appearing in this boundary condition, appears also precisely, is the same factor that appears in the semi-classical thermodynamics. Okay, so finally, you also have to be careful about KK modes or other matter that you might have. But the point is that in this limit, their action has a very large factor in front of them, which is the size of the horizon when you dimensionally reduce, and the interactions are suppressed. So you end up basically with this JT mode coupled to a tower of free fields, and that you can integrate out in ADS2. And integrating them out was basically what Ashok Sen has been doing with his quantum entropy function. And okay, one can take them into account, but the important feature is that they are not going to be temperature dependent, so they will just shift what we call S naught or E naught, given these famous log A corrections, for example. Okay, so before I give the result, can we make a check that this makes sense? And the answer is, or at least one check one can do, is with pure 3D gravity. So the exact result of the gravitational path integral with the boundary torus can be done exactly, that was done by Maroni and Witten, and it's this product of vacuum characters where tau and tau bar are related to temperature and angular velocity. And well, Q is e to the 2 pi I tau, is the very conventional notation. So we can do a Laplace transform of this formula to go to fixed spin and take a near extremal limit. And what you get is this. So you have the e to the s naught, the minus beta e naught. You have this term where gamma is C over 24. This term is precisely responsible for the classical like gamma t squared behavior in the energy or gamma t behavior in the entropy. And the new term is this one loop correction, which depends on the temperature. And this is precisely matches with what you derive from JT gravity. And I'm not going to go over the JT gravity calculation, but it has been subject of several papers over the last years. But it's precisely this, where gamma would be this boundary condition of the dilaton, and in this particular case, it's related to the 3D. In 3D language, in this case, it's the central charge. Okay, so the reduction to JT is valid beyond pure gravity. So other than shifting S naught or E naught, this predicts a universal spectrum near extremality given by this formula. So this formula is nothing more than the inverse Laplace transform of the previous partition function. So it's a spectrum that we expect the near extremal black hole to have. So here there is something interesting. So according to this paper of Preskill, Schwartz, Shapir, Trivedi, and Wilczek from '91, they realized that there is a scale where the statistical mechanic description of black holes was supposed to break down, which is precisely given by this 1/gamma, where in general gamma is whatever multiplies t squared in the energy. It was believed that something went wrong at this scale, and after some string theory examples, it was believed that there was a gap, that there was actually no black holes in this region. But instead, the picture that we're trying to propose is that there is no gap in this case. And instead, what this scale is telling you is that there is a certain gravitational mode, or the scale that this group identified is where there is a gravitational mode that becomes strongly coupled. And now the density of states changes a lot compared to the semi-classical answer. And instead of having the semi-classical answer, which is this dashed line, it actually goes smoothly to 0 as a square root E, where it comes from, where the argument of the sinh is small. And of course, at large energies, this sinh is an exponential, and it gives the area Bekenstein-Hawking semi-classical term. And in this paper, we studied similar analysis in Rice and Northam, and we believe that this is what happens in most examples with ADS2 throw. Now, in case I don't have time to get to this near the end, you can ask, okay, but if I tell you there is no gap, and also it seems like the density of states goes to 0, so the number of extremal black holes is very small, then how is this consistent with string theory examples? How can that be? The reason is that this analysis has to be changed when you have supersymmetry. And when you have a near extremal black hole with a throat with some emergent supersymmetry, there are certain fermionic modes that are becoming massless that has to be taken into account. And if doing this calculation in supergravity, we will find that there is a gap and there is a delta function at extremality. But maybe the lesson is that that might be very special to supersymmetry and not common to all black holes. Okay. Okay, the last thing I want to say is, before moving to the next topic, is that, so I just told you that there is a universal gravitational sector in ADS3. So a natural question is, can we see this universality from 2D CFTs? And the answer is yes. And the only assumptions that are required is large C and to have a twist gap, not necessarily very big. And the idea is that, okay, so in 2D CFT, we can describe a state either in the canonical, like I have been doing, where I fix the temperature and angular momentum, or in a grand canonical, where I fix temperature and angular velocity, or equivalently left and right moving temperatures, which are some linear combination. And the limit we are taking is we want to compute the partition function of a 2D CFT where the very large right moving temperature, so the inverse beta R is going to 0, and a very low left moving temperature, so beta left is very big. And okay, I'm not going to go through the details, but there is a modular bootstrap argument that this partition function is, if you assume a twist gap, is approximately given by the vacuum character in the modular dual channel, and the calculation becomes essentially the same as the Maloney-Witten partition function. And then you can go to fix beta and j at the end of the calculation, and essentially you get the same answer as JT gravity. So so this gives some nice independence check through modular invariance that this universality is also there in 2D CFTs. Okay, so now I will talk about non-perturbative effects. Is there any question, maybe, before I change topic?
Is there any question from anyone?
Okay.
No, Gustavo. You can carry on.
Okay. Okay, so far we have focused in pure theory, we have focused on the BTC contribution to the path integral with the boundary torus, but there are more Euclidean solutions, namely the SL2C black holes introduced by Madsen and Strominger. And they are characterized by a combination of the time and spatial circle that is becoming contractible in the bulk. And Maloney and Witten proposed to define the pure gravity as summing over these saddles, including their quantum fluctuations. And this is the answer they get. So it's a sum of vacuum characters, where the moduli of the torus, there is an SL2C symmetry acting on them. And so you have to sum over it. And the sum, okay, here there are 4 parameters. There are really 3 because it's AD minus BC is 1. But if you look at what are the parameters you really need to identify this circle, the sum is really over C and D, which are coprime and satisfy this constraint. So this is very standard. And the main question is, following holography, can we interpret this partition function as a trace over a Hilbert space in the boundary? And the answer has been mostly no, and there was a lot of issues. And the idea is most of these issues appear near extremality. So the idea now is to use JT gravity to learn about it. Okay, so first we need to understand what is the near extremal limit of the SO2C black hole. And this is very simple. So it's also ADS2 cross S2. So this is time and the radial coordinate. But the special thing, if you look at it carefully, is that there is one defect at the horizon, at the Euclidean horizon. So here time, I normalized it to have period 2 pi, and this is 1 over c squared. So unless c is equal to 1, there is a conical defect at the horizon. Then here you have the extremal radius, the horizon coordinate. You have this U1 gauge field telling you the angular momentum. But there is also this new term that depends on d, this other integer. And this has a non-zero holonomy around the horizon. So also the gauge field is singular. Both the gauge field and the metric are singular. But the important thing is that this geometry is smooth in 3D. And it's kind of like a Kaluza-Klein monopole. You can think of it that way. And a little picture to think about it is that when you go around the cone in the ADS2, you don't end up in the same point in DS1. So when you go from one side to the other, which these are identified, you only go a fraction of the circle. So in order to go back to the same point in the circle, you need to go around the horizon a total angle 2 pi. So, okay, maybe this is a little confusing, but believe me, if you look at it in 3D, it's smooth. And this picture actually also appeared in other examples counting n equals 4 dions in 4D. And yeah, so there were a lot of papers, especially by Sen and collaborators, and then this group making it more precise. So this is another example where including conical defects in ADS2 is important. But okay, but this is the throat geometry of the SL2C black hole. Okay, so now we can compute the correction to the density of states. So we have this sinh, which is the hyperbolic disk ADS2 without defect. Here, EJT is just a rescaling, just to simplify the formula, I rescale the energy. And this is the extremal entropy. And then the first image that you can do this calculation from 3D. I can just take the Maloney-Witten partition function and look at what the leading correction is, and you get this answer. And the problem with this answer is that while this one goes to 0, at the energy goes to 0, this one blows up. It goes as 1 over square root t. And this factor can be positive or negative. And that means that when you compute the density of states, when you're very, very close to extremality, it can become negative. And this was observed in this paper last year. So the first problem I'm pointing out is that the density of states is not positive if you want to interpret it as a 2D CFT unitary. So, okay, so first question is, can we interpret this formula from 2D? And the answer is yes. So first of all, this is the density of states from JT gravity in ADS2 with one defect, with weighting parameter lambda. So it just means you include it with a weight lambda. And with a deficit angle, 2 pi times 1 minus alpha. And it's just useful. I write it this way because it's useful to think of it write formulas in terms of alpha instead of theta, which will be the angle. And alpha equals 1 means no defect, and alpha equals 0 means cusp. And if you compare this formula with this one that you obtained from 3D, you can see that this is precisely the case of one defect with alpha equals 1/2, so defect angle pi, and where this weighting factor is very small in terms of S naught, but has this factor of -1 to the J. And this dependent on J actually can be explained from this U1 gauge field. And okay. Okay, so we proposed a solution in this paper with Henry Maxfield for this problem, and it is if we have been summing over no defect and one defect, then let's sum over any number of them. Why not? The geometry is smooth. Then we should include it. And what I will argue next, so first I want to say the conclusion and then I will explain it, is that when you look near extremality and you can use this reduction to JT, you can compute all these terms with multiple defects, and they have precisely the form such that if you resum them, you end up with this formula, which is well behaved. It's just a square root, similar to as the one coming from the disk, but now there is a shift, a non-perturbative shift in the extremality bound, which is exponentially suppressed in the angular momentum. Okay. Okay, so this gives us a very concrete proposal to generalize the Maloney-Witten partition function that might be well defined. And I say might because we didn't compute it fully in 3D, but at least it solves this problem in extremality, which is to sum over these Euclidean geometries which have multiple. So you can think of it as having multiple points where locally it looks like a horizon of a SL2C black hole. And this is basically the definition of a Seifert manifold. And an open problem is to compute them directly in 3D. And that will be very interesting, especially because it hints at as how to find a solution of modular invariance in 2D CFTs that is unitary and has a large twist gap, which is not easy to find. Okay, so as a little summary of the situation in 3D gravity, pure 3D gravity, this is the spectrum as a function of energy and angular momentum. So the first issue, so this dot is pure ADS3 and this dashed line is the extremality bound. The first issue is this negativity when you look very, very close to extremality for odd spins because it's -1 to the j. And so the solution we propose is to include these Seifert manifolds. And there has been other proposals. The second problem is that there is a negative density of states at the extremal black hole with j equals 0. This really needs a new calculation, and this is a point where the JT gravity approximation is not good, but we expect that the contribution of these Seifert manifolds are not going to be suppressed in any way. So this is going to drastically change the answer, and maybe it fixes this too, we don't know. The third issue that I haven't mentioned that is important is that the spectrum is continuous. So this you could say is also a problem. And the solution is to interpret this as an ensemble average. So we believe that maybe pure 3D gravity is dual not to a single 2D CFT, but as to an average of 2D CFT. And right now I'm going to talk about JT gravity where something of this like this happens. And some evidence of this is a calculation by Kotler and Jensen of this Euclidean wormhole, which comes when you compute the product of partition function that if the theory is dual to a single theory, it should factorize, but the presence of this calculation shows that it doesn't, and that's another feature that is explained by ensemble averaging. Okay, so now we'll talk about these deformations of JT gravity.
Gustavo,
yeah.
can I interrupt for a minute? So are you sure that there are no other Euclidean solutions that might appear and you need to take its contribution too? I mean, how do you know that just considering the Seifert manifold would be enough and there is nothing else?
Yeah. So they're not going to be enough. I don't think there will be enough, but at least you want to find an answer that ideally, I think if you include them, the nice result will be if you get the density of states that is continuous but positive. And then maybe to find this ensemble average, the way I will show it works in JT, you might need to include these extra contributions with non-trivial topologies. I mean, you can have a lot of very non-trivial topologies in 3D. So, I mean, okay, we're trying to do it little step by step, right? So first we want something that is continuum and positive, and then maybe adding these extra contributions that are very complicated with higher genus, or well, higher topologies, sorry, might point out what is the exact ensemble that is describing pure gravity. But yes, that's true. Yeah.
Thanks, Ed. Please go ahead.
Thank you. Yeah. Is there any other question?
No. Please go ahead.
Okay, so this is the action of JT gravity that I already wrote before. When talking about higher, before talking about this case with defects, it's useful to review the exact solution by Schenker and Stanford. So we can sum over topologies in JT gravity. So it looks like this. And it's easy to do the calculation. Well, it's not easy, but it's doable, which is good enough, by Sachin and Stanford, of computing the path integral of this theory on these higher topology spaces. The idea basically is you first integrate out the dilaton. So this imposes the metric to be hyperbolic. So it tells you that R+2 is 0. And then you divide the geometry in a trumpet, which is for any hyperbolic geometry, you can find the geodesic, this dashed line that is homologous to the boundary where the let's say the holographic boundary, and then you use this geodesic to divide the geometry into this hyperbolic surface with geodesic boundary and this trumpet. What Sachin and Stanford did was to compute this trumpet contribution is some function of B, where B is the length of this geodesic that is integrated, and the contribution from this surface that simply gives the Weil-Peterson volumes of this surface. I'm not going to go through a lot of detail, but feel free to ask. But this is the way it works. And so we can compute higher topologies in this way. And the surprising finding of Sachin and Stanford was that this theory is dual to a double scale matrix integral. So if we do the calculation with, let's say, an n number of boundaries of length beta 1 to beta n, then the JT gravity answer, which is supposed to be the left-hand side, is exactly given by an integral over a Hermitian matrix with some probability distribution. And for each boundary in JT gravity, you insert a trace of e to the minus beta h. Sorry, did someone say something? Okay. So the new insight, oh, okay. So the new insight is that the observable dual to JT gravity is a thermal partition function, but averaged over Hamiltonian. So this is an example where we can realize this intuition of the ensemble average that I mentioned before. And this proof is based on the Mirzakhani recursion for Weil-Peterson volumes. Okay. So now a natural question is, can we do the same, but where you add a gas of defect to JT gravity, which is modeling these multiple SL2C black hole horizons? Okay, so that's one motivation, but this is also interesting purely from the 2D gravity perspective, because we might want to know if these deformations are still dual to matrix integrals in this way. So these deformations are parameterized by two numbers. One is this, I would call it fugacity, which is every time you insert a defect, you put a factor of lambda, so it counts how many defects you have. And this deficit angle that I will parameterize in terms of alpha. The calculation can be done in a similar way, cutting along geodesics, and the new ingredient is that you need the Weil-Peterson volumes with cone points. But it happens to be very simple to add cone points by just replacing a defect by a geodesic boundary of length b, and then doing this analytic continuation. And this was proven in these papers that this is the case. At least, well, okay, this is the case as long as alpha is more than 1/2, and I will mention it in a sec. But first, let me say why this is interesting for 2D dilaton gravity. So inserting a defect is equivalent to inserting this operator. You can convince yourself of this by just integrating out the dilaton. So you have in the action a factor of phi times R+2. So if you add this exponential, then this changes R+2 equals 0 to R+2 plus a delta function where the defect is equals 0. So this has the effect of including defects in the sum over geometries. But when you sum over defects in this way, then the result simply exponentiates. And then you end up with a dilaton gravity where you have the JT term, which is this 2 phi, and now you add these exponential terms in the dilaton. So in a way, JT gravity with a gas of defects is equal to a very large class of pure 2D dilaton gravities. Okay, and so I mentioned it's important that alpha is more than 1/2, or the deficit angle is bigger than pi, so there's a sharp defect, because we are cutting over geodesics following Sachin and Stanford, and if alpha is too big, bigger than 1/2, or in other words, the deficit angle is very small, then there might not be any geodesic where we can cut in the most general hyperbolic metric. So here, this is what I'm trying to show here, that we cannot compute the path integral here by cutting and gluing. But I will mention a different method later of how to compute this. So all the cases from 3D gravity have alpha smaller than 1/2. Actually, alpha is equal to 1 over an integer, but we can also compute it in this range using a different method. Okay, so the main question now is, can we do actually the sum over defects to show you that it removes this negativity? And the second question is it still dual to a matrix integral? And the answer to both questions is yes. But first, let's focus on these contributions where we sum over defects without handles. And then we can have handles to see if it's still dual to a matrix integral. But okay, but the sum over these guys can be done by cutting along geodesics. We will take alpha smaller than 1/2. And so we need the Weil-Peterson volumes of these hyperbolic surfaces with cone points and geodesic boundaries. And so we computed this with Thomas Mertens, and there's some work in progress by Timothy Ball. So we did a physicist derivation using the minimal string that I will introduce in a sec. But you can actually do it from first principles. So this is the Weil-Peterson volume of surfaces with genus 0 and n geodesic boundary. This is given in terms of derivatives of this function u of x at x equals 0. And u of x solves this implicit equation. So you take a derivative, then you send x to 0, and it gives you a function of, actually gives you a polynomial in b1, b2 to bn. These are Bessel functions. And the origin of this is that it will become in the old matrix model language, this is the string equation, the 3-level string equation of JT gravity. So okay, using this formula, we can actually do the sum explicitly, and it gives this ugly integral. But the nice thing is that this makes manifest that the spectrum is smooth and positive. So this is from E0 to E. So E0 is the new edge of the spectrum that depends on lambda and alpha, and it's the solution of this equation. In the matrix model description, this equation will precisely be the string equation of JT gravity with defects, where this is the JT string equation, and this is the contribution from defects. And this is some numerical plots of this function. So when lambda is negative, this is very nice. It goes smoothly to 0 at the shifted edge. When lambda is positive, it does the same. But when you go above a critical value, then some weird things can start happening. So we don't understand very well what's the resolution of these negativities. But this is at values of lambda that are beyond the ones we actually need for the 3D gravity application. So this is some interesting feature in 2D gravity that it would be interesting to understand. Maybe there is some phase transition where it goes to a 2-cut or something like that. We don't know. Okay, so we can generalize this to any number of boundaries, and we get this ugly formula with again, a string equation given by this. So by string equation, I mean a function that gives u in terms of x, where that this function is enough to compute any observable you want. And for example, this formula was derived from a Hermitian matrix integral in the double scaling limit by these two groups in the 80s. And it's useful to work with the string equation in terms of, instead of the density of states, and they are related in a simple way. So if you integrate this function u of x, you get the partition function, and then you can inverse Laplace transform and get the density of states. And this was done in the role of the string equation, and the double scaling limit was introduced in these papers. And let me say that the technical way we used to sum over defects was very motivated by a calculation done in this paper by Gross and Migdal, something called the Lagrange method that I learned from there. So that was very useful. And so, okay, so this shows that to genus 0, we can show that JT gravity with defects is dual to a matrix integral. And I'm not going to go through the details, but the same is true actually to all orders in the genus expansion. And there is a theorem of Einar and Orantin that basically, if you read it in the right way, it shows that the JT gravity with defects satisfies the loop equations of the matrix integral. So this tells us that, so this is the same as I wrote before. So the left-hand side is JT gravity with defects now. The right-hand side is this matrix integral. And the difference now with respect to pure JT gravity is that now this probability distribution of Hamiltonians depends on these two parameters, lambda and alpha. But the conclusion still holds this duality. Okay. Okay, so let me, before I finish this part of the talk, let me mention the connection to the minimal string. So that minimal string is a minimal model coupled to the gravity, in this case to Liouville gravity, because it's a non-critical. And we will focus on the 2, p minimal model, because this is the one dual to a one matrix integral. And the density of states at large p matches with the JT gravity one. So if you compute the path integral of the minimal string on a disk with fixed length boundary, you get this cinch of this. And if you take large p with fixed e, you get precisely the density of states of JT gravity. But the density of states, the 3-level one fixes the matrix potential. So if you know that both theories are dual to the matrix integral, and you match the leading order density of states, it means that the two theories are the same. Sorry. At least order by order in the perturbative expansion. So now we can ask a reasonable question, which is, what is the minimal string version of this JT with defects? And the answer is very simple. We just deform the minimal model, the minimal string action by these tachyon operators, which is the minimal model 1, n primary with the Liouville dressing. And when we take large p, we need to take n to scale with p in a particular way, where we keep this alpha fixed. And a check that we can do is that the string equation of this, or the density of states to leading order of this theory, which was computed in these two papers, first to linear order by Moore, Seiber, and Staudacher, and to all orders by Belavin and Samolochikov, or at least conjecture. We can take the large p limit, and it matches precisely with the JT plus defects string equation. So this gives a nice connection between matrix minimal string and JT, and also the formations of the minimal string to the formations of JT. And we can continue with the same. So I was saying before that this JT gravity with defects is only valid when alpha is smaller than 1/2, and we don't know how to do it when alpha is between 1/2 and 1, but we actually know how to do it in the minimal string. So we can take the JT limit of the minimal string for any alpha, and I'm sorry, this is not very nice formula, but it's just to show that we know what the answer is. We can get the string equation, which is completely equivalent to giving the disk density of states as a function of energy and these two parameters, lambda and alpha, for any alpha between 0 and 1. And this is interesting because it's outside of the Sachs-Wenger-Stanford framework, but it's still dual to a matrix integral. And these higher powers in lambda can be interpreted as the defects. Not only there are no geodesics, but also defects can merge if alpha is bigger than 1/2. So we can see all these effects in this new string equation. So this is an interesting, at least for me, application of the minimal string to learn something new about 2D gravity. And this is based on the work in progress with Usatiuk and Wang. Okay, so finally, I will mention very briefly I don't know how much time I have left.
Yeah, we just have a couple of more minutes. And after that, we have a couple of minutes, and after that, we will take questions. Okay?
Okay. Okay, so that's all I wanted to say about 3D and 2D gravity. So in the last couple of minutes, I want to talk about higher dimensions, what happens with near extremal black holes. So I've been talking for the last minutes about non-perturbative corrections, but now we will forget about that and just look at the leading hyperbolic disk the leading contributions. Okay, that will become clear now. The model we will look at is the near extreme Reiser-Nordstrom, so it's asymptotically flat in 4D. It has some horizon of size q, where q is the charge, and it has a near horizon region ADS2 cross S2, where S2 is the horizon. And you can do the reduction to JT, or you can also read it off from the thermodynamics. So you get this. This is the Bekenstein-Hawking entropy at small temperatures. So you get this S0, which is q squared, basically the area. And you get this linear term in T with this linear coefficient that I've been calling gamma, where, as you see, it has the same form as JT gravity, but now gamma, in terms of the for the parameters is q cubed. So okay, so we want to do the path integral in this Euclidean 4D Rhinestone-Nordstrom with boundary condition, fixed charge boundary conditions. So as I said in the beginning of the talk, you need to, we are at low temperatures, you need to identify the massless modes and then take care of the massive ones, but the massless modes are the one dominating the temperature dependence and the shape of the spectrum. So you have this 2D metric in the ADS2 time and radius. You have phi that is like the size of the S2 horizon. You have y that is like the coordinate along the S2. And you have the S-wave reduction of the gauge field, where this A is the U1 Maxwell gauge field that is sourcing the charge of the black hole in 4D. And the 4D Maxwell action reduces, Einstein Maxwell action reduces to the dilaton gravity coupled to gauge fields. In the linear dilaton approximation at fixed charge, it reduces to JT gravity. And this has been studied for a long time, but recently this paper of Nayak, Shukla, Soni, Trivedi, and Vishal, Shakdev, and this paper with Iliesu from this year. So it was mostly studied classically, and in this paper with Iliesu, we try to argue that you can trust this quantum corrections from JT when the temperature is low of the order of the gap, where now the gap is, or no, so there is no gap, but I mean, what people in the 90s call the gap, 1/q cubed. And the only new thing maybe in terms of the reduction is that we keep track of this SO3 gauge field from the rotation, from the Killing vectors of the sphere, which I think was not included before, but one can include it. And this predicts the same shape of the density of states as I mentioned before for BTC, where you have some semi-classical behavior and then it goes smoothly to zero and there is no gap. So finally, the last couple of slides. We know that that's not the spectrum in string theory. So let me briefly mention why what I said is not inconsistent. So something we are studying is near extremal black holes in n equals 2 supergravity in 4D. So we just add the gravitino to the previous theory with the right interactions. And the immersion symmetry in the throat that is broken by this JT-like mode is actually PSU 112, which also appeared in the previous talk. But in this case, it's broken. It's just like the ADS2 symmetry is broken in the bosonic case. And you have to change the calculation because there are new fermionic modes from the gravitino that become relevant at massless at low temperatures. And in this work in progress, we show that the theory reduces to a supersymmetric version of Jacobi Teitelbaum gravity, where you have the SU2 gauge field from the reduction of the isometries of the sphere. You have the metric, the dilaton, and fermions that come from the gravitino in 4D. So let me just mention that you can solve this theory exactly. I'm not going to give much details, but I can tell you later in the question. But you can solve this theory exactly in the disk or in the near the fluctuations around the extremal, the classical solution. And you find this. So before it was just this cinch, but now it has this complicated structure where now J is the angular moment, is the charge of the S2, which is like the angular momentum of the black hole in 4D. And you can see that now the density of states matches the semi-classical, but now goes to zero, not at extremality, but at the non-zero position. So this is the density of states for J equals 0, for example. So it has some very large extremal states of order of e to the S naught. It has a gap of order 1 over gamma, and then it has a continuum that goes to the semi-classical answer. And this, in this case, is 1 over q cubed. And this was derived in the 90s in a paper by Maldacena and Strominger, but this is maybe an improved version of that argument, because in that argument, the breaking of PSU 112 of this superconformal symmetry is not taken into account. And we saw that it's important to take the breaking into account. That's the whole content of the JT mode that is becoming strongly coupled. You cannot ignore it. But fortunately, we see that the qualitative behavior of the spectrum matches with. So this is the spectrum that you find from some examples in string theory. For example, in the similar example is the D1, D5, where you have a lot of extremal state, and then this gap comes from the minimum energy that you need to excite long strings that are wrapped large number of times in the along the brains. Okay, so that's all. So let me briefly mention the conclusion. So we study the gravitational path integral near extremality, and the picture we're trying to propose is that when you go very close to extremality, even of the order of this 1 over gamma of what was called the gap scale, that you can still do it, and there is a clean separation between extremal physics that is computed by, let's say, for example, this sense quantum entropy function, which I didn't talk about, but you have this KK mode, the massive KK modes and all that. And then you have the near extremal physics captured by the JT mode that gives you the shape of the spectrum or the temperature dependence of partition function. So a natural question is that there is a universe. So we saw this universality near extremal in 2D CFT. So can we see it in higher dimensions? It's a reasonable question. Can we push forward this idea in 3D gravity? We pointed out this solution of 2D dilaton gravities as a matrix integral. I probably don't have time, but there is other ideas. For example, when you compute other scenarios. For example, when you compute the Hartree-Hawking wave function in universe with this topology, where there is a very similar. There is something like a near extremal limit that allows to say interesting things about this wave function, but maybe I should end here. Thank you very much.
Thank you, Gustavo. Please unmute yourself and let's thank Gustavo for this nice talk. We have a few questions for you. So I'll start with Ayan. Ayan, maybe you can ask your question first.
Hi, Gustavo. Such a fantastic talk. Thank you very much. So I have a question actually about this this last slide and related to this calculation of Jensen and Kotler. So suppose you could take, I don't know whether this probably makes sense, but suppose you could take some limit where you are having a wormhole sort of connecting two near extremal BTZ, near extremal this torus with boundaries, and then how does this, can you see something directly from the 2D gravity picture? And actually what I really want to ask is this picture that we're saying, this nice factorization between extremal and JT kind of thing, how do you think it will generalize, and whether and how you see it in the 2D gravity way? Is it possible at all?
Yeah, that's a good question. So in general, I mean, these non-perturbative effects, sorry, maybe I should make a distinction. So here I'm talking about the leading disk contribution to density of state, let's say. These higher topology ones, I'm not sure how good approximation they are in general. Probably they are not, but at least in pure 3D gravity, I expect that they are for other reasons. And actually, yeah, Kotler and Jensen computed this Euclidean wormhole, and they take the near extremal limit of their answer, and they get something that matches with JT gravity. So that's another example that this reduction makes sense. That it's so yeah, I don't know. Like, so they get this. There is this universal. They call it the double trumpet in Sandhagen and Stanford. There is a universal answer in 2D gravity for this Euclidean wormhole, which is like the square root of beta 1, beta 2 divided by the sum of beta 1 by beta 2. And that's what you get from taking the near extremal limit of the 3D gravity answer.
But your defect story, the Seifert manifolds, you can also see in their calculation or not? And is there some factorization still? Or?
No, yeah, sorry, I'm sorry, I misunderstood. Yeah, they should include it separately. So you can.
And after that, you will still have a factorization, or the factorization would have to be modified in some way?
The factorization is still broken. I mean, the Euclidean wormhole breaks factorization because it gives a connected component to this two-point function of partition functions. And what we find from 2D gravity is that when you add these defects and you resum, you also get something that breaks factorization. So you get the same answer of a matrix integral, actually. So it's interesting.
Yeah. So is it that the extremal parts factorize and the near extremal parts get kind of entangled, or is it that everything gets entangled to each other? So what I'm trying to say is that if you can capture it something like a JT picture, then this extremal parts will still factorize. This is a sense entropy function that will factorize into separate contributions from the horizons. And then there'll be this near extremal parts which will be somehow connected, right? And this is something that the connected piece will purely come from the near extremal contribution, this temperature dependent.
Yeah, sorry. Even if you don't have defects, you have this Euclidean wormhole in pure JT gravity that will contribute. Yeah. So this
thank
issue of localization is independent of the defect story, and it's not solved by the defects. Yeah.
Oh, thanks.
Yeah.
Okay, so Neil, you may please ask your question.
So hi, I wanted to ask, from the point of view of 3D gravity, the idea of compactifying to 2D to understand this negativity of states, is it something we have to do because 3D gravity breaks down in some region like near extremal region, the 3D description breaks down and some small circle develops and so we have to compactify, or is it a convenience to understand the 3D problem from a 2D point of view?
Yeah, the second. So it's just convenient. So the 3D gravity breaks down in the sense that if you want your theory to be holographic and you get a negative density of states, then you'd say, okay, something went wrong.
No, I meant,
But,
if a 3D spacetime has a very small circle, then one has to go to 2D to understand that because the 3D description is, it's not effectively not 3D anymore. At least this is how I understood, in Ed Witten's talks about when he mentions your work, somehow he seemed to indicate that, and I didn't get that sense from your papers, so just wanted to clarify.
Oh, yeah, sorry, maybe I didn't emphasize it. But yeah, so the size of the horizon is very big, but we are at very, very low temperatures. So in a sense, the ABS2 space is bigger in a way. So you can, you can compactify, but you can also do the calculation in 3D. Or there is nothing that is obviously breaking down in 3D. For me, it's just a convenient calculation because if I do this reduction, then I know how to do the calculation in 2D. But I think one should be able to do the calculation directly in 3D and get an answer that goes to approximate the JT1 and near extremality.
So in that sense, there's no direct 3D derivation of this shift in the extremality bound.
No, that I mentioned is like an open question that I think would be interesting.
And one more small question, sorry. From the 2D gravity point of view, so you solve JT gravity with defects. So that's like an exact solution in the sense it's not semi-classical, right? Because you have one defect or you have any number of defects and you just sum over everything because that gives those are some moduli spaces and you know how to compute their volumes. Is that sort of the idea in 2D?
Yeah, that's I didn't go into too many details, but that's the idea. So this it is an exact calculation in JT gravity. So it's not classical, but it's just that JT gravity is so simple in a way that you can do it. But yeah, you can do it exactly. You need these Bell-Peterson volumes, but you can compute them and some of it.
Okay, thanks. Very nice talk. Thank you.
Thank you.
Any other question, anyone? Okay, if not, then let's thank Gustavo once more. Thank you, Gustavo.
Thank you.
Ayan, are you back? Or maybe we can just wait for.
I'm here.
Okay, then please you can start your presentation. And we are not really doing very bad in time, so although we are just 10 minutes delayed, but I think that's fine. Please go ahead.
Yes. Yeah. Okay, so thanks, Navamita. So before I begin my talk, let me just say something. What I wanted to tell is that there's a nice tradition in Indian classical music that when you become mature enough to become a performer, so that you can not only please the audience, but also please your own guru, own teacher, you actually then arrange for a concert where you sing yourself and invite a lot of connoisseurs also. So although we don't have the same tradition in science, but Suresh reminded me of that when we tried to organize this conference, and he was insisting that I give a talk here on what am I doing. So this will be actually my tribute to my gurus, my grand guru, David Gross, and also to my own guru, Rajesh Gopakumar. And it's interesting that we are speaking in the same session, although it was not arranged that way. It just happened by coincidence because some people had to request some swaps. So Okay, so I'll be talking about something that I've started working on and have been thinking about it quite a while, but it's just got the paper out very recently, and it will be actually hopefully a series of work. And then I thank Tanay for providing this nice illustration, especially many of the illustrations has been done by him, including this one. Okay. So the plan of the talk will be as follows. So I will first give an introduction to why we need a physical model of a quantum black hole and not just simply abstract quantum information theory arguments. And this is something that, and after I motivate the need for a physical model, I will actually describe one that is kind of really simple and successful in many ways. But afterwards, I will then go to a deeper quantum information theory analysis that we are doing with a colleague in our department, Prabha Mandayam, who is a former student of John Preskill. And then we'll discuss what it reveals. And this is something ongoing work, but maybe we can make some definitive statements or sort of definitive statements already. And then I will talk about an improved model, which I'm working on with my other collaborators and also my new postdoc. And then I will go for conclusions and outlook. So the paper, mainly it will be based on this recent paper. I'll also mention some other work which makes this work possible, and then the upcoming works. So for the introduction, we all know that the old black hole after page time is really a very strange object. Half of the Hawking quanta has been emitted. Actually, the physical time scale for a sun-sized black hole will be 10 to the power 67 years. So we can not really see a sufficiently large old black hole at all in reality. But it's strange because it looks very semi-classical if we look usually, because it behaves like it's still a large black hole after all. But if the black hole is some sort of a typical quantum state and half of the Hawking quanta is emitted, what Page's theorem will tell you that if the evolution is unitary, then the entanglement entropy of this Hawking radiation can only decrease after page time. And therefore, if we make a plot like this, we will expect that the entanglement entropy of the Hawking radiation will grow, but then exactly when at the page time, it will take a turn and it will come back to zero. And remarkably, in a recent breakthrough, this page curve actually has been computed for a 2D black hole with some generalizations of that using ADS-CFT. What has been actually computed is a quantum extremal surface, and that's a nice breakthrough. This is something that we expect, but there is something that goes wrong with the old black hole because it looks very semi-classical. We still don't understand how the semi-classical geometry actually emerges, but at the same time, it is quite not, because something drastic happens. And indeed, there is some kind of a secular term that seems to be at work. The context of this whole thing debate is very old, though. So it comes from the AMPS paradox. Actually, it's not AMPS themselves, but there were many other people who contributed to it. But they have made a very sharp statement here. And so what they were able to show that if you look at strong subadditivity of entanglement entropy between these three different parts, early radiation, late radiation, and the interior, and it implies that somehow all the axioms that we hold to kind of tension with each other, especially when it comes to black hole complementarity. So the semi-classical horizon and equivalence principle cannot be valid simultaneously. So there is a tension between the two. And there are many, of course, quantum information theory itself provides some kind of resolution. So one easy kind of resolution, maybe easy or hard, depending how you argue for it, would be that the Hilbert space cannot be factorized after all. And this is sort of what we call in Sanskrit a word called na. It's just a matter of principle. But at the same time, you will argue that we need something in practice, because actually, even from the dual CFT point of view, there are actually some observables which kind of, in some way of talking about it, do factorize and for certain kind of measurements, the old black hole actually is a semi-classical good object after all. So they need some practical resolution to the problem. And Hayden and Harlow gave a very beautiful suggestion, is that the Hawking radiation that comes out indeed carries information of the interior, of course, but to decode it, it would take a time which is exponential in the entropy of the black hole. And so that will take so much time to decode the information that by the time you manage to decode that, the black hole will be already evaporated away, because Hawking evaporation time is polynomial in the entropy. So there will be no really an observable contradiction that you can actually do, because, for example, if you want to verify cloning, that won't be possible, because you could think that you could decode the information, jump into the black hole and see the clone, but that won't be possible, because by the time you will finish decoding, the black hole has already evaporated. And Kim, Tang, and Preskill give a very nice argument, which is a bit more rigorous in my opinion, is that they show that in order to make this argument very precise, all that you need is to show that the late Hawking radiation is pseudo-random in the sense of quantum pseudo-randomness. So perhaps we need some sort of both this Nyaya and Niti, these two ways of resolving this. In fact, these words come in the context of social justice in the discussion of Amartya Sen, for example. So maybe it also applies in physics. So we need sort of both kind of resolutions. So quantum information theory is not only raising paradoxes, but it also tells us what to look for. And this is another very remarkable thing that quantum information theory tells us about old black hole. So it can be kind of modeled as a quantum eraser channel in the following way. So here you have a black hole and you throw in some qubit inside the black hole. Now we know that there is the dynamics that mixes the qubit with the black hole qubits will be very fast scrambling. It will be a extremely fast scrambling dynamics, and the radiation will come out. This is the late radiation. And because you have sufficient quanta already emitted out, the argument would be that immediately after this radiation comes out, you could decode it. You could decode using some other operator that has no access to the interior, but only to the early radiation and to the late radiation. And then you could decode out the message. And so the message can be decoded like this. And this operation V will be related to this unitary operation U. And this should be possible at the time when this thing is scrambled. And this scrambling time is for a black hole we know is RS log RS. So so this is called information mirroring, because somehow an old black hole able to do this. So whatever you throw in, because sufficient quanta has already been emitted, it will be able to mirror. It will immediately be able to reveal the information of what goes in. But the actual information of how it has been formed will be very complicated and will not be so easily revealed as the earlier argument of Hayden and Harlow tells you. So this is a sort of thing that quantum information theory gives us. However, many of these things are not really completely clear unless we make a physical model after all. And well, the first question is why simple observations see that the exterior and interior after all decoupled and we can distinguish them from each other. So this is something that we need to understand in a more precise way. But there also, this is sort of an old question, but there are some other questions, of course, that with the physical model can only tell you. And it's that for the information mirroring, we need some class of observables in this radiation system, which are exclusive to this mirroring, because you have to do the mirroring without any access to the black hole interior. So these observables in the radiation will not reveal actually any information about the interior at all, because if you have to know the interior to do the mirroring, you have to wait for exponentially long time, right? So you should be able to do the mirroring without knowing anything about the interior. So there should be class of observables within this radiation that is exclusive for mirroring, and from where the information of the infalling information should come out fast and easy, but they should not allow the decoding of information without knowledge. Okay, I mean, and this should be possible without any knowledge of the interior. The decoding process should not depend on the knowledge of the interior. On the other hand, there should be some sort of complementary observables, if you like to call them this way, which will encode the interior, but only in a very complex way. And then the question is, what is a principle that allows us to find such decoding algorithm and blah, blah, blah. And even before going on, maybe we should ask how we can even ask all these questions in a more precise, rigorous manner, because this is a kind of heuristic way of asking questions. After all, maybe there is no factorization of the Hilbert spaces and all these things. Okay, so it turns out we do have one, and a kind of physical model, which I'm going to present to you just now, just after this. And this physical model is a model that has lots and lots of microstates, which are essentially stationary solutions, static and stationary solution. And these are with and without hair. And the hair would be a very important part of the story. This hair is nothing but soft degrees of freedom that only live on the horizon. And this model will have this interesting energy absorbing and relaxation property. So if you start from a microstate and you shock it by throwing some qubits at certain locations, what happens is that such a microstate would go to another microstate very, very quickly. And it will also absorb almost all the energy. So if you take the quantinuum limit, it will absorb actually all the energy. Otherwise, it absorbs, even for a 5-site model, it absorbs a 99.99% of all the energy that you are throwing in. So from the point of view, so unless we're able to resolve this microstate, it will actually behave like a classical black hole because it's just quickly relaxing. We can only see the overall mass there, and it absorbs everything that you are throwing in. So the hair on the horizon actually also is interesting. First of all, the hair on the horizon can decouple from the black hole. And it is the decoupled part that is kind of moving on the black hole, which is without affecting it, provides the key to decode this infalling quanta and this to do this act of mirroring. And inside this hair, there exist observables. Not all observables are like that, but a certain class of observables which are blind to the interior and through which you can decode the infalling information just after the whole system relaxes and goes to another microstate. And then at the same time, this hair will decouple and carry away this information. And actually, we will talk about how this now reflects into the Hawking quanta. Essentially, there'll be some kind of entanglement structure, which I'll talk about, which tells you that the mirroring will also happen in the Hawking quanta, but I'll come to that later. And the dynamics of a system is sufficiently pseudo-random so that the information of the interior is indeed encoded in a very complex way, and many questions can be posed precisely by QIT. So this is sort of where we are going to. And initially, we will not worry about how we can account for the entropy, but finally, I will tell you about that. Okay, so this is sort of the kind of quick introduction to our motivation for what we are doing. So now I will talk about the simple and successful model, but maybe I can now pause and take questions if you have any already. Okay, if not, then hello, am I still audible?
Yes, yes.
Okay, thank you. Okay, all right. Okay, so maybe I should move ahead. Okay, so now I will talk about this simple model and that I already advertised. And I would just simply ask you to go to and listen to this very nice song called That Old Black Hole. There's a nice group called Dr. Dog, and there is this delightful song. And here it says that, okay, you have to just, I don't expect you to believe me, but everything is all right. So I just simply tell you that I'm trying with a very simple model, and apparently it will not account for entropy or something. And I don't, of course, claim that it's sort of an analog model, and which can be improved, which I will claim later, but hopefully it will turn out to be all right later. Okay, so this is a cartoon of what our model is. So it takes inspiration. It only takes inspiration, that I will say. It's not a derived model from anywhere, but inspiration is from essentially the fragmentation of near extremal geometry to multiple throats by these Birol instantons. And this is pointed out by Maldacena, Michelson, Strominger, but not much work probably has been done on this. But one of the main things that you see is that when this black hole throats get very close to each other, this fragmented black hole throats, this is all an Euclidean computation. These instantons have a lot of zero modes and abundant zero modes, especially in this boundary of moduli space. where they come close together by some sub-Planckian distance. Now, this inspires a lattice model because it's an Euclidean picture. We have to go to a Lorentzian picture, so it's an inspiration only. And so the inspiration is that we simply think of this this fragmented two-dimensional black hole throats as sort of hard degrees of freedom, which crystallize, form a crystal. And the dimension of this lattice that is formed is essentially a dimension of the black hole horizon. So if it's a one-dimensional horizon, it will be a periodic chain kind of thing, and if it is a two-dimensional horizon, it would be some two-dimensional lattice. And the soft degrees of freedom, which are the zero modes, essentially carry gravitational charges, and they would kind of hover on this lattice, will be kind of mobile on this lattice. This is sort of the rough intuitive picture that we start from, and of course it is not derived from anywhere, but let's see from how far we get, how we can construct something that is at least makes sense just from this sort of heuristic intuitive picture. Okay, so these are the ingredients then of our, so we talk of a one-dimensional horizon. So in continuation of today's session, it will be sort of a fragmented ADS3 kind of picture. And so the ingredients would be SYK type quantum dots, which are dual to NADS2 throats. So each of these ADS2 NADS2 throats will be dual to some sort of quantum dot, which is SYK type dynamics. And the degrees of freedom that describe these things and simply a time reparametrization mode, because once you know this time reparametrization Ti of u, you will be able to compute all correlation functions. So the time reparametrization captures all correlation functions of the non-trivial state. And this time reparametrization simply takes you from the vacuum correlation functions to the non-trivial state correlation functions by conformal mapping. So these are the degrees of freedom, is simply time in a way. And the mobile gravitational here simply carries as SL2R charges, the same as the charges of the unfragmented ADS3 throat, but they are now mobile. And crucially, the full system must only have one overall SL2R symmetry, which corresponds to the original horizon geometry. So this is the original SL2R symmetry of the ADS3 throat, and so this is a kind of the model. Now these quantum dots, because they are NADS2, they also carry their own SL2R charges, and they're related to this time reparametrization modes, time reparametrization variables by this formula. So these are essentially the Noether charges of the system, of the gravitational system. And I define my SL2R invariant dot product like this, and the mass of each black hole of these NADS2 throat will be simply the Casimir of this SL2R charges. And this is nothing but the famous Schwarzian derivative of Tu with respect to u. And this u is the common time of the experimentalist, which is common to the whole setup. And Tiu are the individual reparametrization modes. So this is sort of just simply a cartoon description. Now, I would rather be quick with what is actually happening in the NADS2 geometry. So if you want to get a picture, so this is how the NADS2 actually is capturing in a geometric way the non-trivial state that I'm talking about. So you can start from a vacuum state of the quantum dot, and that will be dual to, for each throat, that will be dual to a simple geometry like this, which is pure ADS2. Now you can think of a time reparametrization. Now this time reparametrization at the boundary can be extended to some Eddington-Finkelstein gauge-preserving bulk diffeomorphism. And this bulk diffeomorphism, you can do it in any gauge. I'm just choosing Eddington-Finkelstein gauge because that's good for simulations. And then this Eddington-Finkelstein gauge-preserving bulk diffeomorphism is this. So you see at the boundaries at rho is equal to 0, and actually everywhere, at all values of rho, time is simply redefined like this. And if you do this diffeomorphism, this geometry then goes to this, where m of u is now appears as some kind of ADM mass. And crucially, m of u is related to this T of u by the Schwarzian derivative of T of u. And actually, this diffeomorphism gives a cost to the action, this because there's a present of bulk dilaton, which is sort of takes a fixed renormalized value at the boundary, and that is the key feature of NADS2. It kinds of give a cost to action. So as long, of course, it's up to SL2R. So SL2R is always a symmetry of this particular throat, but the coupling will break, of course, the individual SL2 symmetry, but I'm coming to that later. So now the dilaton in each throat actually takes a rather simple form in our case. And what actually drives the time reparameterization is a self-consistent null matter field, which is traceless and conserved in this geometry. And it takes this particular form. And the derivative of the Schwarzian, that is the derivative of the mass, the time derivative of the mass, is simply given by this null energy momentum tensor, TUU component of it. In this, that's such a brief description only. And there are some other nice identities which are helpful, is that if you take the time derivatives of this SL2 charges, they will be proportional to the Schwarzian themselves. And that is easy to see why, because after all, in the pure gravitational theory, these are conserved and the time derivatives have to be proportional to the equation of motion. And the equation of motion should be essentially m prime or Schwarzian prime is equal to 0, because of fixed mass has to be a solution after all, because the thermal state. So this is what we expect anyway, but it's something that we find is by identities. And also you find that Ti prime, if I look into this equations, I can write Ti prime as a suitable combination of these objects. And so you see that Ti prime is a suitable combination of these 3 SL2 charges, but these combinations only have Ti's, no derivatives of Ti's. So it simply tells you there's a very nice kind of simulation scheme that you can talk about, that instead of simulating all the Ti prime, Ti double prime, Ti triple prime, you could simply evolve the SL2 charges and evolve and then compute Ti prime from here and then evolve Ti itself using this. So this is a scheme that we found in a previous paper. But of course, this is one way to say it. Is also another, it's sort of complicated because it doesn't work exactly as I said. From the point of view of numerics, you have to actually redefine these TIs into something else. But anyways, you can read, I will mention that paper. So now let me come to the equations of a model. The equations of a model is as follows, that each of the masses of the throats evolve like this. So these are the SL2 charges of the individual, of the heart, of the ADS2 throats. And they, if you look at this term, this is essentially like in the continuum limit, it becomes a Laplacian of QIs. And this couples to, with the SL2 invariant dot product, it couples to this mobile gravitational charge QI prime. And this mobile gravitational charges actually are kind of freely moving by this linear equation with these specific sources. And so now you might think why we come up with such specific equations. So firstly, you will see that the first equation is almost like a diffusion equation if you take a continuum limit, provided Qi prime acts like some sort of a diffusion constant. So indeed, it is sort of becomes a constant at late time, but still this is not exactly a diffusion equation, but it's a sufficient approximation to diffusion equations such that it is enough for relaxation and decoupling. But you have to always set lambda equal to greater than 0. That also you can see to make the total energy positive, you need lambda greater than 0. So you need lambda greater than 0, and then it really works like almost like a diffusion equation, but not exactly. And if you look at this equation, this is simply is responsible for the mirroring. So after there is a relaxation, there are some component of this hair degrees of freedom, this mobile gravitational charges which decouples from the interior. And one of the things that always decoupled is essentially, you can see if you add all i's, sum over Qi double prime will be equal to 0. If you just sum over all I, they all cancel out. And therefore, some I Qi prime, this object is essentially a constant, is a primordial kind of monopole charge that always stays with the black hole and essentially is responsible for some kind of diffusion constant like behavior. And but it's highly non-trivial that you can do some decoding without knowing the interior. Of course, that doesn't come out from our equations directly, something that you see. And we think it's most likely possible that we can actually add higher derivative terms in the hair, or change this model by accounting for higher order interactions such that these phenomenological features will be retained. It's simply the simplest thing that can I think I can claim after some experience is something like the simplest set of equations that can do all the job that we require them to do. So the hair actually must be quantized. So although we are thinking of this large n limit, we are taking large n limit in each throat. So the n-raised to gravity is semi-classical, but the hair actually should be quantized. But what we will do for now is to take some coherent states of the hair. So the hair will also admit classical description. Okay, this is something that I already said before, so I can skip. The total energy of the system actually split into two parts. And the first part is simply the sum of all the black hole masses, which I will write it as sum m. And there is the sum of the hair. And this is simply the hair energy is nothing but the kinetic energy plus these gradient terms. And note, there is no interaction term between the two. So this is actually crucial because the energy can be neatly compartmentalized into something interior and something exterior. We'll see more on this soon. And this is actually important to make sure that, okay, that we can see that it behaves like a classical black hole at the end of the day in the continuum limit. So now let us look at the microstates of the system. Maybe here I can again be a little fast. If you want to, the slides will be there if you want to go through the details. So this microstates are nothing but static stationary solution of a model. So you have to simply find all static stationary solutions of a system. And that is something we can readily do. So first of all, we need the right-hand side of this equation to vanish. And these are linear equations. So they have unique solutions. And the unique solutions are simply that these mobile gravitational charges are locked with the ADS2 throat gravitational charges in this specific way. But if it is locked at one time, we have to make sure that it's always locked, remains locked. And there are two ways to achieve it. One is that you simply say that one of the components is homogeneous. And why homogeneity is important is that if it is homogeneous, then okay, we'll see why homogeneity works. Or you could say the other primes things are zero, or this other in the other directions is zero. And and if it is homogeneous in one, okay, if it is homogeneous, then it's quite clear that if you start with such a configuration, it will remain like that because all of them would get some extra correction like plus some something u. So it will, so only these things, so these locking will be still preserved. But this homogeneous part, you could always rotate because there's an overall SL2 symmetry in the system, only one. You can rotate and make it in the zero direction without loss of generality. And this is important because, but after you do this, you have exhausted the overall SL2 symmetry. You cannot do anything further, but you can always do that. You can always put the homogeneous QI prime in the zero direction. Yeah, but you also need the masses mi primes to be zero. And for that, you could also see that you can easily see that what you need is to put one of these things in the same homogeneous direction as QI prime is. And then all of these QI zeros should be the same value Q, whereas the other plus minus components can be random and constant numbers. So, and then what you can easily realize that what you can do, you can always add some decoupled oscillations on top. So these are the kind of homogeneous components of QI 0 prime, but you can always add some extra term, which simply can propagate without affecting anything, affecting the black hole configuration at all. And they follow simple kind-Gordon equations. There should be an equal to 0 term, which is not here somehow. Okay, to summarize, the microstate solutions are simply like this, that you have all the QI, all the interior things are simply Q, some homogeneous, and the plus minus components are random and constant. And the hair has kind of separation into a monopole term, which is simply alpha U. And then there is a radiation term, which is decoupled from everything and simply hovers without affecting anything. And the plus minus components are locked with the black hole, and they are stationary and constant, static and constant values. Okay, so there are this neat separation into a monopole term, a radiation decoupled term, which is simply free and propagating, and the other is a locked term, something that is locked with the interior. Now, the beautiful thing is that if you look into the energy, of course, as I said, it splits into two parts, the sum of the black hole masses and the kinetic energy of the hair. But the hair energy itself actually splits into three parts. One is this, because of the dynamics of the system, one is a potential part, the other is a monopole part, and another radiation part. Now, this is important because the potential part, which comes from the locked charges, this actually is locked with the interior, so you cannot really access it. Whereas this monopole term and this radiation term are accessible, and they also neatly separate into two. So this is sort of the energy in the early radiation or primordial energy, and this is sort of the radiation energy that comes from after decoupling. And there is also something nice I have to skip, maybe because not so important, maybe. So there are some other inequalities that you have to impose because Ti prime and Ti double prime have to be continuous for the equations to make sense. And therefore, and interestingly, if you have the two possibilities, and interestingly, if you choose one of them, then all of this Ti primes has to be greater than 0, which means that all the arrow of time of all the sides points in the same direction. So something like the uniform arrow of time sort of emerges from our model, and it doesn't something that you put in, and we of course choose the future direction. If you choose the other one, it will then point backward in time. Okay, so now we can talk of the ensemble of microstate solutions. We simply fix total mass m and this homogeneous component q and the monopole charge alpha, and these are the three things. And other things we are simply randomly we can choose. So we can choose all the other masses such that they add up to this mass, and then qi plus minus such that each gives the right Casimir, but they are random and subject to the inequalities that we discussed. So then we can just start from a random initial microstate, and we can add the hair on top or not add it. Okay, so now we have to see whether our model really behaves in a semi-classical way. So whether we reproduce this energy absorption and relaxation properties. So essentially what will happen if we start from a microstate and shock it, then it will simply go to another microstate very, very quickly and absorbing all the energy. This is something that we need to check, at least whether it is true in the continuum limit. So unless we resolve the microstate structure, we should be able to see a kind of classical black hole. So to shock, we simply start with the same equations. The only new thing that we add is we sort of perturb. So we throw in energy or inject energy into one of the throats at different times. So these are UIA at the times where we are injecting the energy, and EI is this amount of energy that we are throwing in. And in the black hole geometry, what is happening is this is still a null matter, except that it gets an extra contribution, and these are delta function like. So these are null shocks that goes inside each throat at specific times carrying specific energy. So it's like an ordered list that we are sending in inside. So for a single shock, we see this nice thing that which I already advertised is that if you throw in shock, so this is the total energy. Of course, we are injecting energy will jump. So there's total energy conservation after that. However, you see all this energy is absorbed by the total black hole mass. Actually, it is not true. It's a 5-side model. Actually, 99.99% actually goes inside this black hole mass, and in the hair, it only takes a very tiny fraction of it. And of course, this fraction goes smaller and smaller as we take the continuum limit in a systematic way. And now you see this nice relaxation. So because we start from a microstate, after all, as I said, this Qi0 in any microstate solution has to be homogeneous. So it starts from the homogeneous value. Now, when you shock it, it sort of starts moving here and there, but then they again converge on a different homogeneous value. So you might think why it again converges in the 0 direction. It could have changed the direction, but actually it's a monopole charge, which is primordial and is always constant, reminds the black hole what frame to choose always. So it always goes back to the same frame, and this is what we see. On the other hand, if you look at the plus minus components, for a single shock, it's kind of goes to it saturates to different values. And the most important thing is there seems to be no relation between where we started from and where we ended. You might try to think there may be some pattern, and you might guess a pattern, but if you just change your shock or change your initial geometry, all the pattern disappears. There is no uniform pattern at all that you could find out about that can relate from the initial to the next. It's a kind of a random dynamics that is happening, but we still need to quantify it. And this is again the behavior of the masses. So it's the 5 masses of the 5 individual throats. They again saturate to some constant values after the shocks, after the relaxation. And then the dynamics is really pseudo-random as it sees. And the final microstate actually also has decoupled oscillations. Okay, so now it's time to, this also happens with multiple shocks, and the dynamics indeed has this energy absorption and quick relaxation properties. It has pseudo-randomness, but it needs some quantification, and decoupling of exterior and interior dynamics happen dynamically. So it goes going from one microstate with decoupled hair to another microstate with decoupled hair, happens dynamically, and the energy of the hair is conserved on its own in the continuum limit. It's not exactly true if you're not taking the continuum limit, but it's true in the continuum limit or in the large volume limit. The final macro state always has a decoupled hair oscillations, which is important for the mirroring. Okay, so now let me come to how the mirroring is actually happening. So again, this is kind of the circuit diagram that we have in mind, which is very similar to the diagram that I showed earlier in the talk of the quantum eraser channel. So here we have this interior, we shock the interior, shocks plus interior, and it interacts with the hair now. And after this, all this interaction, the radiation component decouples, and there is already some kind of radiation component, but only with the radiation component alone, without any access to the something that is locked with the black hole, we can decode and get the shock information. So this is how our information mirroring should occur. And essentially, this is a nice picture of that. So now we have to look into this decoupled radiation. And essentially, if you look into the system, it will have this, you have to simply solve the Klein-Gordon equation, and you to find for a 5-site model, there'll be 2 positive frequency modes and 2 negative frequency modes. And then there'll be 1 0 mode also. So essentially, this the 0 mode is essentially nothing but the monopole term. And we have to only look into this positive frequency modes. And the amplitudes and phases of the oscillations are very complex and carry information about the interior, of course. And due to pseudo-random dynamics, it's very hard to decode the interior, of course. In fact, we don't understand how to decode it yet. However, the phase differences of the normal modes mirror the infalling qubits, and they behave approximately as if we started from a mixed ensemble of microstates. That is, the decoding procedure will not require any information about the interior from where we started with. But we need to know this early radiation because it gives a primordial frame where this decoupling happens, this 0 frame, which is simply chosen by arbitrarily by circular rotation. But to know the frame, we need to know this early radiation too, like in the usual story of quantum circuits. Okay, so now what we are going to do, we are going to decode 1 shock and 2 shocks and essentially decode these locations and sequences. But before showing the decoding protocol, let me give you a picture of how this normal mode frequencies look like, the Fourier transforms. So you see that there are 2 of them. And if you look, and this is only a plot of the amplitudes, not of the phases. But you see that the amplitudes are rather random and there is no pattern. And it's very hard to understand where the information comes from. The phases also look very random. But miracle happens when you take the phase differences. And here is the miracle. So you started from a highly asymmetric and non-trivial state. If you look at different, all this randomness and weirdness goes away, and you find some sort of beautiful symmetry. So if you put a single shock, you see that the phase difference is something like this between the 2 positive normal frequency modes. But around it, there's a nice symmetry. So if you go to the left and right, they're almost equal. And then if you come, of course, it should be almost equal, not exactly equal, because it's only an approximately, it will still be kind of contaminated with some information of the interior. But the important thing is the contamination can be reduced by some noise cancellation. And then you see there's a very, very nice, beautiful symmetry, almost approximate symmetry. So you see that from where you know that this is where you shocked in. Now, if you have 2 sides, you also see a similar kind of pattern, but not exactly symmetric. But what you always see is that the 2 sides are where the phase differences are minimum and maximum. And if these are neighboring sites, then the minimum phase difference was shocked first, and the maximum phase difference was shocked later. And if they're not nearest neighbor, then the opposite is true. Then this is true. Whatever you start from, whatever initial state you start from a random state. You choose your initial conditions randomly. This is always true. And then if you this is always what we find is true. And so you see that there are these 2 different things. But now the one with the smaller site was shocked later. Smaller phase difference was shocked later, and the other one with the maximum phase difference was shocked earlier, if they're not neighboring sites. Okay, so this is a simple example. So now we can go to, so I think I'm almost exhausting my time. So I will be now, I think I have around 5 minutes.
You started late, so you can take like 5-7 more minutes.
Thank you. Okay, thanks, Navamita. So I will now go to this QIT analysis, and this is actually one of the beautiful things of the lockdown. The lockdown, of course, was very mentally challenging, but one of the nice things that came out is I started discussing with my colleague, Prabha Mandyam, who was a former student of John Preskill. And while we were actually in the campus, meeting in the campus, we were so busy that we couldn't discuss. But of course, the paper also came out, and she also became interested in the whole topic. And she herself has thought about it. So we started understanding what all this means, because after all, we are talking of just classical information. The classical information is encoded in some ordered list of where you are shocking things. But after all, we are interested in the quantum information. But of course, she tells me that, look, I mean, even all quantum information analysis first start with classical information analysis. So this is not really, this is the start, just as a starting point is very good. So let us see what happens. And so first of all, we have to understand what happens if we put in the Hawking radiation, right? The Hawking evaporation actually is a very slow process, right? Which is very slow on the time scale of the relaxation that we are having. And so it can be readily incorporated also, because we can compute the Hawking radiation in each of these throats, provided the matter is exactly like in this new works of Almheri and others, where they were able to do this computation explicitly, provided the matter that couples to JT gravity is a CFT. So it will, since it's a slow process, is not going to change our story very much. But the main thing is that we are computing now this quantum extremal surface, which is actually just as a computation is not that hard, because it's simply kind of a simple principles are already there. And so we can also obtain the page curve. But the beautiful thing is that now, because we have a fragmented geometry, the quantum extremal surface will also be fragmented. It's not, even if you take the continuum limit, it will not go to something smooth. It will be smooth if you take some averaging perhaps, but it is not going to be extremely smooth. It's not that easy to take a continuum limit in what we're doing. I mean, it's certain things we can be sure, okay, we can make certain statements in the continuum limit for certain class of things. It's not yet clear whether we can actually make a statement about the quantum extremal surface in the continuum limit, but the hope is that we can do it. Okay, but all the while we are talking of the hair, but not the Hawking quanta, right? So now what we need to do is to quantize the hair and study the full dynamics in the large N limit. And the nature of entanglement is the question about what is the nature of entanglement between the hair, Hawking quanta, and the interior. And it's our conjecture. It will be of course, we can actually do the calculation and verify it, or verify it to some extent, at least have some measure, some test of, do the simulation and see, hopefully. But the conjecture, it will be the GHZ type. So what is the GHZ type is that if you take any two together, it is maximally entangled with the third, which means that if you trace out any one of the three, you will produce a completely disentangled or unentangled state of the other two. So this is a GHZ type kind of entanglement. And it's sort of a simplest example of a perfect tensor. And so now, because there is this GHZ type entanglement, you could think that the Hawking quanta will be maximally entangled with this two things, hair and interior, the system of hair and interior. And we know that in the hair, there is this mirroring that is happening, right? So what we need to know is what observable in the Hawking quanta. So it's a statement about operators, not really about states now. What observables in the Hawking quanta will have maximal mutual information with the phase differences of the decoupled hair oscillations that does the mirroring. If we can find that, then we will be able to then understand how the mirroring is actually happening in the Hawking quanta. And taking advantage of this entanglement, which we need to quantify, well, we need to see whether this mirroring is actually happening with complete fidelity or not. It may be that if the entanglement is not of this type, then it doesn't really happen with complete fidelity, right? So we hope that it is our model, it will be GHZ type. Okay, but how do we avoid these paradoxes? To avoid paradoxes, we have to actually make sure that the encoding in the Hawking quanta of the interior would be rather complex. And to make sure of that, we have to actually compute this quantum extremal surface. So one of the things that we're hoping for is that if we manage to take the quantum extremal surface in the continuum limit, the deviation from the semi-classical geometry, which has been computed in all these remarkable papers, this deviation from those computations will have only very fine substructure with a fractal-like or something. And then, of course, it will be rather complicated or kind of way to find out how this encoding is done. But still we need to answer this question, what is the code subspace? And finally, although it looks very elementary, but still a profound question is, after all, in what sense there is some kind of decoupling so between interior and exterior. So one of the things I learned from Prabha is that decoupling actually means something very precise in quantum information theory, is that for simple class of observables, it will the state, entangled state would look like a product of the marginals. So this is something that's been very well studied in many other contexts in quantum information theory. And what she tells me is that if the quantum chaos could be the answer even for this sort of decoupling, even in the presence of Hawking radiation. So if you want to have any hard question, you should ask Prabha, who is probably there in the audience. I hope so. So then the next question is the decoding also universal? So what we see is the phase differences is a thing that does the mirroring. And that seems to be very robust, because phase differences have, one can argue, are very robust kind of things which can capture the information that we need. But however, there will be some kind of complementary observables that you can use some kind of complementarity idea in the context of information theory. There is a very big literature on how you can generalize this notion of complementarity in quantum information theory, and that could help us to understand what kind of observable is the code subspace that will do this and capture the interior. So the interior reconstruction ADS CFT can look like this, that here should be described by some kind of dual CFT degrees of freedom, which are infrared, and the Hawking quanta are more perturbative, and together they are important to capture the interior. So the interior, so if you just trace out the interior, these two will be decoupled. So the perturbative and non-perturbative dynamics are kind of factorized. However, this factorization is not true. Like we know in a proton, we think that there is a factorization of, into this, in the DIS amplitudes, okay, there's a factorization of non-perturbative and perturbative, but certainly in full QCD, you don't expect a factorization, right? And sort of, the interior is sort of the invisible hand. So I come back to this picture, which I first flashed earlier. So the black hole interior is sort of the invisible artist, which kind of composes a perfect tensor state out of this this perturbative and non-perturbative degrees of freedom. So it's sort of like some sort of invisible thing that you have to do a very fine-grained measurement. So if I do DIS kind of thing on a proton, I won't see this black hole interior kind of thing. I have to do something much more refined and complicated in order to understand the black hole interior. So that is kind of the big picture message that probably is coming out. So I just now have 2 more minutes. Sorry?
Maybe you can just finish in like a couple of minutes, okay?
Yeah, I'm almost done. I will just try to just have 2 minutes, okay? So right now I'm just going to tell you about some ongoing work that we are doing with improving this model so that we can have a sort of understanding of the entropy. And this work is being done by Arnaud Kundu, also Tanay again, and Giuseppe Policastro and Abhik, who is now joining as a postdoc by an Indo-French grant. Okay, since I don't have much time, I'll simply tell you what I'm doing is that, what we are doing is that we now have a holographic CFT. So this is the hair now. So instead of just SL2 or hair, you now have a Virasoro hair. And then these ADS2 throats are now kind of strings that live in this ADS3 that is emergent from the holographic CFT, and they live here. And essentially they're described by exactly what Rajesh was talking about, this SL2 or West-Zumino-Wheaton model, except that you now have a network and you have to figure out what you do here at the junctions. Is the first quantized version would be like that. And the second quantized version, you could even talk about transition between 2 different string networks. Yeah, so you have some kind of quantum interior, but this SL2 or West-Zumino-Wheaton model, which is quantized, is now interacting with the JT gravity that lives inside this network. So this is sort of the picture that we are trying to build. And the interesting thing is that there is some kind of nice coupling that you could do between these 2 systems, which we call kind of democratic couplings, which I kind of invented during my work with semi-holography. So these couplings essentially think that these 2 systems are kind of isolated systems on their own, but they have some kind of but they're self-consistent isolated systems. So they simply see 2 different effective metrics or 2 different things. But anyway, I don't want to go into those details. It will take us another talk. But it seems when we do calculations with this kind of couplings, we see that when we take the mutual coupling to infinity, the full system always goes to a full CFT. So the whole system should go to some strongly coupled CFT when we take this kind of mutual coupling to infinity. So that would perhaps capture the universality class of some real black hole, some real extremal black hole. Otherwise, if the couplings are not infinite or finite, it will only be capturing a near extremal one. Okay, so I'm not out of time. I'll just simply end with and nothing more to say that other than we have probably a reasonably good phenomenological model of a quantum black hole, and then, but perhaps what is one of the biggest lacking in our work is that we do not have a nice way to connect to the asymptotic region from the horizon, away from the horizon. And I don't know yet, maybe if we can make some connection of an improved model with fuzzballs, this can help. And but this is simply a speculation. Maybe with some dimensional reduction of fuzzballs, we would be able to make such a connection, but I don't know yet. Because indeed you have some sort of ADS3 throat in a fuzzball. Okay, so this is just simply, I just want to end here, and thank you very much.
Let us all unmute ourselves and thank Ayan for this talk. Okay, so please write your questions for Ayan if you have any. Or in fact, you can just probably unmute yourself and ask your question directly also, since this is the last session, I mean last talk of this session, so it's probably okay. Okay. In case we do not have a question, then let us thank Ayan once more for this talk. So thank you all for having such good talks, and I thank all the participants also for asking questions and making this session live. Thank you, and with this I conclude this session.
Thank you, Naumita. Thank you, and thank